A few people on the call already. We'll give it a few minutes, guys, just to let everybody else. We did say we're going to kick off at 9 o'clock, but we will just wait a few minutes. We'll do a quick overview intro and we'll get going from there as well. Just want to say a quick thank you for everybody who's taking time out of the day to join us, whether you're joining us for part of the day or the full day. It's much appreciated. It's even more appreciated if you don't know who me or Joe are, and you're just here on the off chance you're trying to learn something, and we'll see if we go from there. We will try not to disappoint. For the benefit of the guys who don't know us, I am Sean Hanlon, structural engineer with about 18 years experience. I'm a director at SPHStructures, and I met Joe through ARAD, which is the Association of Rooftop and Airspace Developments, last year. I was asked to be technical committee lead there, and a couple of the guys there asked me to reach out to Joe regarding some technical stuff we were doing. And obviously structure and fire are the biggest issues when it comes to existing buildings. Now, Joe was one of those guys whose name I'd already seen around the industry, and I knew our paths were going to cross at some point. But I'd say rather than crossing, they kind of just crashed together, and we've been running together ever since in the same direction, which is kind of what brought us here today. Does that sound about fair, Joe?
It does. You said earlier you were going to say how we met, and I was thinking, how did we meet? I can't remember, but that is it, isn't it? The committee and kind of, yeah, paths crashed. So yeah, that's absolutely fair. It's a good version of the story.
Yeah, wasn't a blind date or anything.
No. Yeah, no, absolutely perfect. I'm as you're talking to Sean, I'm keeping an eye on the chat. Someone's had an issue with some sound, but it looks like it's resolved itself. So thanks, Phil, for putting Mitchell on. So hopefully everyone's got us. So throughout the day, Sean, as you're talking, I'll keep an eye on chat and questions and things. Everyone do keep that chat going if you need, and vice versa, Sean. We can do that as well, can't we? So yeah, perfect.
Yeah. I'm going to launch straight into overview for the day. Let me just share my screen. Go from here. So, you, Joe. Sorry. So we split the session up into, we split the day into two sessions. We have a morning session and an afternoon session. We did this because when we first broached the subject of doing this, and we threw it out on LinkedIn back in January, there was two distinct kind of groups. People wanted to dig into the risk assessment stuff and didn't necessarily need the morning session. So the morning session was aimed at upskilling ability and like knowledge sharing in the morning, whereas some of the more experienced engineers might already know the stuff we're going to cover in the morning. So that's where we've come with two sessions. If you haven't signed up, there are two links for each session. If you haven't signed up, you haven't got the link for the afternoon one, don't worry, we'll throw it up on the chat here in the morning, copy it, and then you'll be ready to go from 1 o'clock. So after this, I'm going to launch straight into competency from 9 till 10 each. We're going to try to keep each section to about an hour, talk for about 45 minutes, and then whilst I'm talking, Joe will keep an eye on questions and the chat, and then we'll try to do questions chat by the end. Joe's then going to launch straight into intro to fire, and I'll switch over to the chat and the questions. We're trying to hit 2 hours straight this morning, and then we're going to break 15 minutes before I come back and do the intro to structural engineering, which should take us up to about 12:15. And then we'll go lunch for about 45 minutes. When we come back, Joe's going to kick off the fire risk assessment, and that's going to lead into the structural risk assessment. And I've got John Carpenter joining us from 2 o'clock as well, talking about soft hazards, which will lead into what I'm talking about. That's going to be a good couple of hours again. We're going to break for another 15 minutes, and then we're going to open it up to the discussion point right at the end of the day from about 3:15 onwards. There are discussion points that we want to come back to that we have highlighted in each of our presentations. So, but if there's anything you want to ask, anything you want to talk about, if we know it, we'll try help, and we'll open it up into the discussion as well. So that's the rough plan for today. Again, any questions, just throw. There are no stupid questions today. The aim of today is to knowledge share, try learn, and try push what we're doing a little bit further, and just share it with you guys and see where you guys are coming from as well. Ready, Joe?
I'm all good to go, mate. We can launch straight into your session if you're happy to. Screen share all works okay there. So if you want to share screen, I'll keep an eye on Q&As and everything. And good to start with competency, I think, aren't we?
Cool, all good. All right,
fantastic.
Cheers, guys. Let's just come out of that. Good. to this one. Why is my taskbar on the side? That's annoying. There you go. That's better. Okay, right, competency. I'm going to start here with the UK spec that was published back in November last year. This is the reason that we're here today, basically. So I picked this up probably end of November, December, sent it over to Joe and said, have you read this? And he hadn't at the time. And I said, basically, I think they're asking for a knowledge share. Do you fancy a note swap? And he said, yeah, can do. Do you mind if we're doing that, do you mind if we get some of the staff members involved? I was like, yeah, it's fine, no bother. Well, if we're doing that, should we invite some clients? I was like, yeah, it's fine. Well, if we're inviting clients, we might as well open it out to everybody else. I was like, Joe, it's fine. We'll make a day of it. Hence why we're all here today. I'm going to backtrack on competency half a step and go back to the CDM regs 2015, because competency is something we should all be doing anyway. So this was published back in 6th of April 2015, the last revision of this, and in clause 8 they talk about general duties. Clause 8.1, designer including principal designer or contractor including principal contractor appointed to work on a project must have the skills, knowledge and experience, and if they're an organisation, the organisational capability to fill the role that they are appointed to undertake in a manner that secures the health and safety of any person affected on the project. So even before we get going, we should be demonstrating skills, knowledge and experience. Part 3 of that clause states that a person who is responsible for appointing a designer or a contractor to carry out work on a project must take reasonable steps to satisfy themselves that the designer or contractor fulfill the conditions of paragraph 1. So not only have we got to prove that we're competent, we have to demonstrate we have the skills, knowledge and experience to do the job. The person appointing designers and contractors must also ensure that they're appointing competent people. Okay, this is a theme that's going to run all the way through this. It's been there for the past 8-9 years. We should be doing this as an industry anyway. Now, I think it's unfair if I sit here and preach about competency without at least suggesting how we do it or how we approach it. So we send out our competency documents, both personal and organisational, as part of each fee proposal that we send out. So when we get a new job in, we look at it and then we go back to the client and say, right, we have looked at your job. This is what we think. Here's the fee for it. And here's our competency that says, this is what we think. This is why we think it. And this is the fee to take it on. Even if we don't get the job, at least we turn around and say, look, whoever you go to is fine, not a problem, but make sure you're asking for their competency. They should be giving you this information as well. And then this is your responsibility. This is our responsibilities. And at least that way, even if we don't get the job, we've done our best effort. We're pointing in the right direction and we're getting the client to ask the right questions, even if they're not part of the industry. So in terms of organisational competency, for us, it's predominantly skills and knowledge. Our experience, you can see through the website, our LinkedIn, our Instagram, even and because there's only 2 of us at SPHStructures, our own personal experience portfolios feed into the SPH competency as well. So we kind of link it in with that. And then in terms of when we adopt it for the organisational, we're looking at, okay, what is the engineering council? Where is their hierarchy? How does that play? What does it take to be chartership? Who's chartered? Is that important? Who are we chartered with? What standards, regulations, design guides apply to us as an organisation? How do we follow them? How do we coordinate design? So when we work with fire, architects, M&A guys, contractors, subcontractors, what's our coordination process? What does that look like? How do we do that? How do we identify risks as part of the CDM bricks? Like, what does that look like? How do we establish that in the drawings? How do we check? Checking's a big one that I want to kind of touch on later in the discussion as well, because, and I've asked about on this, and please correct me if I'm wrong, but I think structural engineering is the only discipline within the industry that has a Cat 3 check as part of their design for high-risk buildings. Cat 3 checks are checked by an independent engineer separate from the organisation who are doing the design. And I think that's really important. Has its flaws, still here and there, but I think we're the only ones who do that. And I want to know if anybody else in the industry do a Cat 3 check as well for higher risk buildings. And then we also demonstrate the process of design and construction. So again, this could be aimed at people who are in industry as well as people who are in industry and don't know certain bits, but at least it gives a good first impression to go, okay, good, these guys have got the ducks in a row, they know what they're doing, great, okay, nothing to worry about there. From a personal competency point of view, again, this is about 16 pages. For me personally, I'm touching on, okay, yes, I am chartered, this is what I did to get chartered, this is the core objectives that I use. I know a little bit about law on contracts. I know a little bit about materials. I know a bit about conceptual design, detailed design, the construction process, the environment, this, that, the other. And I've demonstrated that I know enough about that to get me chartered. And then I've sat a day-long exam that says, yes, I can work under pressure and just churn out stuff as well. That's basically hitting a level. That's what chartership explains. In terms of my knowledge, it's training, it's your CPD evidence, which most governing bodies are going to call in anyway. But we put it here and I can say, right, last year I did 600 hours of training. I went on that CPD, I read these documents, I did this. Year before that was about 400 hours of training. Year before that was about 300 hours of training. So even straight away, clients or whoever's appointing us can say, okay, good, they're still training, they're still progressing, they're still staying current. And obviously, we include the experience in terms of our CV, where we've worked, what we've done. Yeah. And I also put in a separate portfolio to this as our portfolio of evidence in terms of the projects we've worked on. So it might be visual condition surveys, it might be reports, it might be examples of calculations, might be typical drawings, calcs, whatever we do, and then project specific information. So you can already see, okay, right, they've got the organizational competency, personal competency, and the experience that goes along with it. Now, I think once you do this once, you only really need to update it, maybe every 6 months, every year tops. But this goes out with every fee proposal. Yeah. And within our fee proposal, we include these two clauses that we spoke about earlier, saying it's your client's responsibility is that you've got to appoint competent people. And then competent people are defined as this: skills, knowledge, and experience. And so I'm going to say industry should be doing this. I don't see many examples of this, but the Building Safety Act is now bringing in competency with a vengeance, so to speak. We're all seeing the impact on building surveyors and what they're having to jump through right now, but it does impact designers and contractors as well. Impacts us through secondary legislation. So the changes to the building regulations, which came in on the 1st of October 2023, they've got a whole chapter on competence. So, and these guys are basically reiterating what the CDM regs already say, with one exception. So clause 11F part 1, any person carrying out any building work or any design work must have, where the person is an individual, skills, knowledge, experience and behaviour necessary. Where the person is not an individual, the organisational capability. Part 2 of that clause is the same but for contractors. So again, that's already reiterating, echoing what the CDM regs already say, with the addition of behaviour. Now, behaviour, I'm taking to mean following a code of conduct from your institute. So speaking on behalf of, say, the Institution of Structural Engineers, I know within the code of conduct there are clauses in there that say you should be behaving necessarily. You can't be calling out engineers for doing bad work. You have to act appropriately. So I think if you're a member of an institute, you could probably get your behaviours competency effort there ticks via that way. I know REBA have been training their guys, additional training on the behaviour aspect for this recently, but I don't know how that would look from, say, a contractor or M&E or the fire guys, or what you guys do, or how you're going to negate this additional requirement. And then if you backtrack a little bit into clause 11E of the regs, this regulation applies where a person P is proposing to use any person A to carry out any building work or design work. So that's just reiterating that the client needs to make sure people they're appointing are competent. This bit's new. And this is the bit that I want to discuss later on at the end of play today as well, because I think it opens up a whole can of worms. And this is where designers, especially designers and anybody else, might get caught out. So Clause 3 is the requirements in paragraphs 1 and 2 that we've just spoke about do not apply to an individual T who is in training to fulfill those requirements. The person who asked T to carry out any building work, or as the case may be, any design work, must ensure T is adequately supervised when carrying out the work. Okay, what's in training? Yeah. So at what point do you start being in training? Is it when you attain chartership? What if you've never attained chartership? What is adequate supervision? Is it one-to-one supervision? Is it one chartered engineer for supervising a team of 6 guys? How does this work where you have 4 or 5 engineers in training around you in a bigger firm, for instance? Should trainees be working on higher risk buildings? Does this raise questions about the ability to check a job? So should it only be competent engineers checking each other's work? And what about if you go between cross consultancies? You're doing Cat 3 checks. How do clients ensure the right people are on the right job? I think this opens up a can of worms, and I think it's going to hit the guys who are competent but not necessarily chartered, because I think chartership will help you in this instance that you've already demonstrated. For instance, in my personal CPD, my personal competency stuff, I've already shown that I've reached a level in terms of materials, laws, contracts, basic design work, detailed design work, construction appreciation, all these kind of bits. If those guys haven't done the portfolio for that, how's it going to affect those? So that brings us on to the Engineering Council and why they produce these documents. So top left, we have the UK spec for HRBs, and then that was published in November. And then in December, there was 3 further documents, annexes, fire, structural, and building services that were addition to this. Now, excuse me, in terms of the hierarchy of where this sits, your recognised standards here at the bottom, that is going to be your chartership, your code of conduct, and everything, whatever you're within your institution. So that's already expecting your base level of standards. I would say, I think that's chartership. I think if you've hit that, you've demonstrated you've hit this level, you should be working at this level already, and then you should be acting a certain way with the code of conduct and your behaviour aspect of that. UK spec sits above that. These are additional requirements on top of what they require there. So again, I touched on the non-chartered competent engineers and how they're going to achieve this. So who's responsible for this assessment? Is it the clients? Is it the Engineering Council? I know that the Institute of Civil Engineers, the Institute of Structural Engineers, ICE and the iStructy, they're combining to produce a joint register. So if you're on that register, you are seen as competent to be able to work on higher risk buildings. I don't know if Fire, M&E and everybody else would be doing a register similar to that. And I don't know if clients are going to demand that as part of working with them on high risk buildings. Now, I also don't know what the repercussions of using someone not on the register. I don't know if that's a risk to the client and they take that chance. So maybe the non-chartered competent engineers will be hoping for that clause as well. But I don't know how hard that's going to be enforced. So I think this is opening up a can of worms at the minute, and we need to be careful about how we tread through here. Now, when you open the UK spec, there's 3 points that are talking through it. You have the incorporated engineer, the technician, and the chartered engineer. We're going to focus on the chartered engineer today, but each discipline have their own requirements of what we should be demonstrating for the additional work. Now, when you turn the page, you've got 4 sections basically, and these 4 sections run all the way through the book. So your competence, which on the left here is AA, knowledge and understanding. There will be certain points, normally 1 or 2 points per area. So in this case is 1 point, maintain, extend, and develop, same theoretical approach. A rough scope. So, and this is every engineer. So this is structural, fire, M&E. We all need an appreciation of a knowledge and understanding of fire science, structural safety, fire prevention, public health, building fabric, building services. And then the HRB specific criteria over here, there's 3 points that we definitely have to demonstrate. There's another 7 points if they apply to you as well. So that's 10 points that we've got to demonstrate that we have competence in and we know. So when you go through the rest of the UK spec, there's 5 areas. So knowledge and understanding AA, BB, CC, DD, EE. when I read this, I think AA is the technical aspects. That's the upskilling. This is the note swap. This is why we're here today. I've got to learn about fire. I've got to learn about structure. And this is what we're learning. And then we go away and we demonstrate this. You might not get everything you need to learn today, but at least point you in the right direction, give you an idea of how to pad out your competency, and then you can go from there. B, C, D, and E, I think that's stuff you should already be doing anyway. It's not necessarily technical, and I think if you're already doing it, it's not too bad. If you're not already doing it, it's quite a lot of work that are involved. Now, I was talking to another engineer on this because I was going to go from this and go, right, AA, we're going to focus on AA, and then I was going to shoot straight off and only talk about AA. But another engineer read this, and his interpretation of it was, is it not similar to the principal designer role in that we still do our work, but then those who are competent or who have demonstrated their competency go on the register and they basically sign off and check our work? And I was there like, I don't think so, because it defeats the point. How does the client know if you're competent to do the job in the first place? And I think if you're doing that route, it defeats the point of trying to upskill the industry, and it just creates a bespoke checking group within the industry. And I don't think that's the point. So I'm going to elaborate on these points a little bit more, because it has been interpreted that way. So AA, every chartered engineer working on the project needs to demonstrate an understanding underpinning technical principles, fire, structure, life safety. Great. Note swap, rule in here. Get that. BB, design, development, solving engineering problems. They're pushing the legislation here. You've got to know it. Responsibility management, leadership, understand the process. So your golden thread, your safety case reports, etc., as well as demonstrating behavioural traits such as whistleblowing and escalating safety risks in a correct manner. I would say that's your cross, your confidential reporting of safer structures, and knowing how to report critical safety aspects, like immediate safety aspects, to the HSE. How do you raise them? If you see something wrong, how do you shut down a site, for instance? They want evidence of project management, both technical and commercial here too. Communication and interpersonal skills, general act professionally stuff, but some specific items in there about dealing with residents. I suspect that's aimed at existing HRBs, although they don't specifically state it. And then your personal and professional commitment. You're basically keeping up to date with the codes, legislation, best practice, CPD stuff. So when you go through AA, and you combine that with the structural annex. So I'm using the example of the structural national annex here. And on top of the 10 points they want you to look at in the UK spec, structure have a further 18 points that we need to demonstrate on point 1 alone for knowledge and understanding. And as part of those 18, we have understand hazard identification for HRBs. That's fine. Eliminate or mitigate these risks. That's your ERIC, the event control process and hierarchy. Understand root causes that affect the structure or fire safety of a building. I would say that's your visual condition survey, or if you're doing a new build, it's understanding where the main risks are and what could go wrong. Identify barriers in place. It could be access and all that kind of stuff. And then assess major accident structural safety hazards. This one I've highlighted. Understand the difference between performance-based and compliance-based approaches. They don't come in here and say there's a difference between how you should be approaching new buildings and existing buildings other than this clause. This is the only thing I've seen that alludes to the fact that you have to take one approach to new buildings and one approach to existing buildings. Performance-based is code compliance. I call it prescriptive. You follow codes, you do what it says, you get a nice shiny building at the end of it. Sorry, that's compliant-based. You follow the codes, nice shiny building at the end of it. Performance-based is you've got to look at how the existing building's working. Some existing buildings don't work to code. They don't even work to their old codes, let alone the new codes. So where are you drawing the line on safety? How are you assessing that building? A lot of engineers make the mistake of trying to shoehorn in existing buildings into compliance with new regs, and they don't work. And I think that's where you're seeing a lot of the news bulletins at the minute with evacuations around higher risk buildings around the country, because I think people are panicking and trying to assess old buildings to new codes, and I think that's where they're going wrong. And then obviously we've got to look at disproportionate collapse against fire-related hazards as well. Now, on behalf of all the structural engineers out there, I'm having a quick moan, because in the national annexes, we have 18 additional points to do. Fire have 9, building services have 8 additional points. In each of the annexes, structure or structural are mentioned 24 times within our annex, but it's not repeated through the others. Considering we've got 28 points that we need to pick up, which is a lot more than the other annexes, why isn't appreciation structure being mentioned in the other annexes, especially if we're doing a knowledge and understanding? That just seems out of proportion to me. I think that needs changing going forward. But to be honest, I think the UK spec was quite good. I didn't think it really needed these annexes. It's essentially creating a bit more work for us as well. So going into BB, back into the UK spec, now that you're aware of the annexes and how they feed in as well, BB is the design, development and solving problems. Now, there's 2 points within this that we need to cover. So point 1, which is down here, is just retyped up here, take an active role in the identification and definition, project requirements, problems, opportunities throughout the building lifecycle of HRBs. That's your specs. That's you doing the job. That's going through, raising a design, development, and everything else. So this is when I say this, I think you're doing this anyway. I think this is just your job. Most engineers should be doing this as a regular day-to-day occurrence anyway. Now, the scope of what they require here, especially for point 1, they're asking for you to know construction legislation, related guidance. Excuse me. Now, in terms of the construction legislation, they want you to know, great, okay, do you know what the Building Act of 1984 is? Do you know what the Building Safety Act of 2022 is? Do you understand the relationship between acts and regulations? Do you know which building regulations, which approved documents are applicable? And then in related guidance, they want to know if you know the plan of work, so the REBA plan of work, Building Services plan of work. I would throw in the I/T plan of work there as well, because it's different from the REBA, and it adds an additional work stage between stages 4 and 5 for the structural engineers. So if I'm an architect, if I'm a fire engineer, if I'm building services, do you appreciate what we do there extra before we get on site? And then for scope 2, they're asking for British and international standards, good practice specifications. I would say that's all your national specifications. So in structure, we have national specifications for timber, steel, concrete, piles and embedded retaining walls, all stuff that we can reference as good practice throughout the industry. And then your maintenance requirements, which you should be raising as part of your CDM regs anyway. Now, I would say you should know this anyway. People know this. This is how you do your job. It's just demonstrating it. That's the problem. Now, again, as I said at the start, it'd be remiss for me to sit here preach about competency if I'm not going to share how we do it. So on the left, we have the basis of structural design. This is Eurocode BSEN 1990 or EC0, as it's commonly referred to. And we use this as a check-in document. So within each of the codes, you have principal rules that have to be adhered to. So these are the ones with little p's at the end. And then beneath those, you have application rules. Now, the application rules give you a way of demonstrating compliance with the principal rule, but you don't have to follow the application rules. If you know another way of doing it, you can go that way, but it should give you the same output and get you back to the principle. So there's a big problem with our industry at the minute with over-reliance on software. People churn through, hit a button, churn numbers, computer says yes, off you go. The problem is not all the principal rules are picked up in those software packages. So if I'm looking at a drawing, I'm picking up drawings as part of a check. I know especially if I just get a rule of calculations printed out, I'm there like, okay, have you read the codes? Do you really know what's going in? Okay, have you addressed this principle rule? What about this principle? What about this principle? And when you start looking at all that, it should build your design. It should feed into the design anyway. And then in terms of the regulations, this is CDM regs. We made a conscious decision a while back that basically anything that we get asked from site or within the design team, especially from site, goes onto our drawings that we issue at site. And one of the biggest arguments we always had, especially with the smaller contractors, was stability of structures, responsibility, temporary works, and contractor design portions, so such as steel connection design, timber connection design, and all those elements. They're taken from the national specifications. But what we did was we typed up the CDM regs. Now this is just 2 pages. This is the first page. And we highlighted bits that are either applicable to ourselves or applicable to contractors. So we say, right, this is our responsibility. Our responsibility as designers is to highlight any design, construction, and maintenance risks in the project. And we do that, and on the second page, we show how we do that. So they're included in our GAs, they're included in our details. And half the time, most of the questions that come back is because they hadn't looked at the drawings. And we found this is a really powerful tool in terms of, no, we're covered here. This is where it says, and it's no longer our opinion, it's code says this, regs say this. And then we review this. I'd say we probably reread it every 3 to 6 months, just to make sure, just to refresh it, because you can't remember everything, but I know the gist of it. So that's how we demonstrate compliance with legislation, codes, and everything else. Moving on to CC, you're looking at the responsibility management and leadership, the UK spec. So this is understanding the process, golden thread, safety case reports, and the like. The scope for it explains duties of engineering in relation to HRBs, roles and responsibilities of the key duty holders. I would say I'm having a chat with a lot of clients at the minute, so they fully understand their duties and their responsibilities, and that comes down to communication as well, which we're going to come on in the other points. And then integrate understanding through life management and maintenance. Again, I think that's really important for existing buildings, and it's almost the first question we're asking that when we're appointed on HRBs. And then we've highlighted this bit, which is challenge others where duties are not being met. This, I've highlighted it because it almost contradicts code of conduct, especially ours. So we're told that we almost can't call out or challenge. You can challenge engineers, but you can't call them out. And I think that's where the difference is. And just the last point before I move on, competence needs building safety managers. I know it's great. Okay, so it's just reiterating competence throughout everybody who you appoint on the job. But going back to challenge others where duties are not being met, I think there's, okay, this. Read a job book. This is what architects work to. So if an architect asks us to do more design work or asks us to do certain bits that are typically outside of our scope, I can say, no, that's not our role. It's not within our scope because you haven't issued a responsibility matrix, which you should have done at stage 2. If it's on there, great. We could have priced it. We could have gone through that and we could have worked with that. I've seen one responsibility matrix from an architect in about 5 years. They don't normally kick it out, probably because we use it to beat them over the head with. Same for the M&E guys. That includes stages of work and roughly what they kick out. So for us, I went into this looking at, okay, how are M&E guys showing their drawings? Do they look down on the floor? Do they look up on the floor? Some engineers we've seen combine their drawings to look up and down. That's confusing. So for us, we just wanted to try and understand where they're coming from. And then obviously for the fire guys, it's reading through your codes and understanding, okay, how are you guys approaching risk assessments, for instance? Where's the collaboration there? What's your output in terms of this? Don't necessarily know this as well as I know my own structural codes, my own structural guidance, but I know the gist of it. I know enough to push back on where and know what to expect at each design stage, for instance. And I think if you can demonstrate that you've done this and you know where they're coming from, it gives you the bigger appreciation of the design phase. And this is what they're kind of pushing for. So when we come into communication and interpersonal skills, we're going to say it's the general app professionally stuff, some specific items in here about dealing with residents. So in terms of the scope, it's requirements, obligations to communicate, consult with and respond to occupants, residents, demonstrating evidence of oral, written, drawn communication. You should be doing that as part of the chartership anyway. It's reports, it's drawings, it's calcs, it's easy. And then communication within the project for client teams. Communication across the life cycle of HRBs. That actually made sense requirements. Now, I'm going to throw in one aspect here, going back to the first point about obligations to communicate, consult with and respond to occupants, residents. I've stressed the point that we cannot be scaring the bejesus out of residents with terms like your building is at risk of disproportionate collapse as a possible fire considerations. These people are non-technical. They do not understand the nuances of how much of a risk this is. If you say the building's at risk of collapse, you're going to cause widespread panic. The best way we kind of approach it, and I've told my clients to hold off on communication as long as they can, so we can manage this process a bit better, is saying, look, your building hasn't changed, just the regulations have. Regulations are here to make sure that all the existing buildings are safer. And we're going to make assessments. We're going to make collapse assessments. We're going to make fire assessments, amongst other things. And we're going to add additional safety measures in where they're needed. Okay. And this is how we're going to approach it. And if they want to come back and understand which terms are, we think that should mitigate the risk of panic within the buildings a little bit more. But it needs to be very carefully managed. I think you've got to be really careful, especially us as structural engineers, to go around and go, your building's at risk of disproportionate collapse, everybody out. Don't get me wrong, if the building is at risk of disproportionate collapse, everybody out, we do it. But that is it's a big responsibility there, especially when you're dealing with 40, 50, 60, 70, 80 units of people, all their families and where they're going to go. And then we'll come on to the last point, EE. So personal professional commitment. So keeping up with your codes, legislation, CPD stuff. So you have an obligation to consult all the engineers, us via M&E. We have an obligation to consult, listen to the resident's voice. How you do this, again, it should be, I would say it's more aimed at existing buildings, but how you do that with your clients, whether you do it through a series of webinars or online calls or in person, don't know. I think you need to plan that out before you start engaging with the residents, though. So they're clear about the communication lines, and then you can structure it to see where you go through and raise questions that way. We all do have a duty of care to the residents. That needs to be reiterated, and then you have to adhere to codes of conduct, which IFE, I'm sure they have their own. M&E, I'm sure they have their own, same as us. And then the legislation guidance that applies to HRBs, there are specific regulations out there. There's 6, for instance, that apply to high-risk buildings. 3 are more procedural in terms about how to register buildings, how to manage the buildings and everything else. And then 3 of them are quite technical. So it's worth being aware of those. And then you've got to demonstrate competence to drive cultural change, which I hope we're doing through this and trying to push the industry in the right direction, sharing info. And then all that, excuse me, is fed back into your competency documents, your personal and your organizational competency. And then we are basically adding, our intention is to add AA as an additional page onto our competency documents. So we're already doing B, C, D, and E, and it's seen as building that. So that's where we're from, and this is where competency, and this is why we're here today, and this is what we're going to learn from. So I think that should cover it.
Brill. Thank you, Sean. Hope you can hear me again now. Are we back?
Yeah.
Fantastic. Really good run through. There's been a good kind of stream of chat in the meeting chat, and I've pulled out some questions to give to you, Sean, as well, if that's all right. If anyone has any questions on what Sean's just talked about, pop them in the chat as well, and I'll pitch them to him. I think everyone else is muted, aren't they, Sean? So I don't think we can bring people in, but I'll relay questions as they come through. Cool.
We can do. I was going to plan on doing it for the discussion at the end, but we can play about it now if you want. Basically, I think if you click on whoever it is, you right click on that, more actions, you should, I don't know. I'll figure it out.
If anybody wants to come in live, we'll figure it out. Otherwise, I've written down a bunch of questions, Sean, from the chat, so we'll start on those. Right, okay, so Andrea, starting with a question, and it's one that I really like, actually, because it's one I'm asking myself in my business at the moment about the point you made, Sean, about legal requirements and should we make clients aware of them. So how much of a duty do we have as consultants to tell our clients what their legal responsibility is? And I suppose I've added this bit on, this isn't Andrea's wording here, but do we have a defence if they've not asked us to do something and that's a duty they have, but we've not made them aware of it? I suppose, where does that sit currently? I guess it's an opinion-based question, but what do you think on that?
I think there's a bit in the CDM that says it stipulates domestic clients rather than professional clients. So I think if you're a professional developer, a professional contractor, or whoever else, you should know your legal requirements going in. I think if you're dealing with domestic clients who aren't necessarily aware of all the codes and legislation around it, you're duty bound to make them aware of what their responsibility is. So that's why we put the competency in on fee bids and say, look, this is your role, you should be appointing competent people, this is why. But I think that's the line that's drawn. I don't know the code specific, but I'd double check the CDM regs for that.
No, it's an interesting point, because I've talked about this recently with my team and when I'm teaching as well, that if I'm presenting myself as somebody who's competent, I should be aware of all the legal duties both I have and my client, and I should be relaying that to them. But also the client now has the legal responsibility under the Building Safety Act to make sure they're appointing competent people. So by virtue of that, they have a duty to know their own requirements as well. So there's this kind of little loop, isn't there, about who's responsible for it? But ultimately, not a defence, is it? You've got to still make sure that they're aware of, and it's their duty. Perfect. Paul's just raised a point, and it goes back to a question I wrote down about how do we demonstrate behavioural qualities as opposed to something you can go and sit a degree in and get letters after your name. How do we demonstrate those behavioural qualities?
I would look at Reba at the minute to see what they're doing, because I know they've been doing additional training on this, but I don't know what that training looks like. But I would, at the minute, we're just relying on our code of conduct. So I know our code of conduct says behave appropriately, don't call out engineers, set the other. There are behavioural standards that they require of you. So at the minute, I'm throwing that in until I can get back and reread the Reba stuff and see what they're doing, and then I might pad it out with that for the time being. I don't know how that looks like for other disciplines, though.
I mean, I would answer in much the same way. I'd look to the code of ethics I have via my institute to say what is expected of me and what am I expected to demonstrate, and benchmark against that. I actually find myself looking a lot at the code of ethics of other institutes as well. So I read the iStructures, I read Reba and what they're saying to see if they have another take on it. Because again, as a competent practitioner, I think that the code of ethics come from my institute, and that's great, and that's my minimum. But actually, if someone else is doing something that I can demonstrate, I find myself beholden to that, at least for my own personal ethics, I suppose you could say. But it's inherently more difficult, isn't it, to demonstrate a behavioural quality than I've got a level 5 qualification, level 6, level 7, whatever it is. It's the harder one, and perhaps to put on a fee proposal, if you know what I mean.
Yeah, I think if you lay out your ethics, that look, me as a professional, this is my responsibility, this is where I'm coming from, and I'm a chartered engineer with this association. They require this of me. And I think even if you put that out there and say that, it at least the clients could use that as something to hit you over the head with. It's at least putting it saying it's at least making you accountable for something. I think it's somewhere to start, and I think we'll probably dig into it a bit more over the next few months as people start trying to figure out what this looks like. But yeah, code of conduct, check what Reba are doing, and we'll try to go through there.
Absolutely, yeah, and the rest of industry as well, I suppose. I look to contemporaries in industry to see what they're doing as well, and learn from those people around me a little bit as well. Another question from Andrea, actually, and it's one that I asked you yesterday as well, Sean. So I'm glad it's come up, and hopefully you can drill into this a little bit. And this probably answers the question about whether fire do this. So, what is a Cat 3 check? So, can you describe in a bit more detail the Cat 3 checks? And it got sort of pulled apart, or not pulled apart, but discussed in a bit of detail in the chat there as well. Cat 3 checks for HRBs versus non-HRBs, and just the definition of what that Cat 3 is. But also, can I then ask as well, is there a Cat 1 and 2? So is this a scaled thing? Do you get to the Cat 3 that's completely third party, or just can you elaborate on that for the fire engineers in the room?
Yeah, so this was almost a kind of question for you guys as well, because I was thinking about this after our chat last night as well. It's like, do you guys have consequence classes for buildings? How do you categorize buildings?
Define consequence class, because I assume that means in the event of an incident, as opposed to just as a standard, grading buildings as they stand there.
Yeah, so consequence classes, we have 1, 2, 3. 1, low risk. So I think your agricultural sheds, like very low risk people, 1 or 2 people in there every year. If there's a risk of collapse or anything goes wrong, it's likely nothing's going to happen. Class 2 buildings, and this is in our approved document A, for instance, if it kind of gives you an overview of how we approach for each one of them. Class 2 buildings are basically residential up to 4 stories. And you have certain tying requirements, certain safety requirements that we have to make those a little bit safer. And then if you go and say residential 5 to 15 stories, that's 2B. So 2A is the smaller stuff, 2B is that. 2B also includes, let's say, 2-story schools, because we care about little people more than we do adults, and they are our future. So for 2B, we had additional time requirements. So 2A will be horizontal, 2B vertical. We make sure the whole thing's tied. And then class 3 buildings are typically 15 stories and above. I think that's changed now with HRB. I think they've halved that limit down to 7 stories. So, and then we work on that basis. Now, depending on that basis, what consequence class your building falls into dictates the checking requirements that you apply to that. The class 1 buildings, it's a self-check. We believe you, it's not risky, great, off you go. Class 2 buildings, it should be someone within your organization, but not the design team. So it's a fresh pair of eyes, but you can keep it in-house. And then if you're doing the riskier stuff, as you go up the ladder, say Cat 3, this is why we call it a Cat 3 check, consequence class 3, then you're looking at a different organization, and basically you're sending them over architect's plans, scope of work, and maybe the loading at tops, and you're asking them. So for instance, if I'm doing a 30-story tower, I might be going, look, Joe, can you check this for me? You might run a quick model, make sure my floor plate thicknesses are the same. You might be looking to make sure you get the same reactions on your columns, and you'd be like, yeah, great, works, thanks. That's Cat 3. And then you come back to me and go, I agree with you here. What about this? And it's just a safe pair of eyes over it. Now, I was thinking about it last night in terms of if we're reducing the safety level down from 15 to 7 stories, then does this trigger a Cat 3 check? Because I know I treat all existing buildings as Cat 3 because of the risk levels involved. So that's, and then we had this chat yesterday and I asked you, do you guys do a Cat 3 check? Do you guys send out your designers to other engineers? And is that part of the industry? And we thought, and that's why we thought engineers are the only ones who do this. It is a really powerful tool. It's not without flaws, but that's the premise behind it.
With whom does that responsibility sit for the Cat 3 check? Is it you as the engineer to get a contemporary in industry, or is it client or approver that would ask for a peer review that's independent of?
So Cat 3 checks typically trigger, the clients will know they need a Cat 3 check anyway. So they'll be aware that they have to go to another engineers, and it might be a quarter or a third of the fee, because there's a fair bit of work involved in there. So you're expected to do something. And then if, for instance, I've been Cat 3 checked twice on a couple of refurb jobs. One was about 8-story, I think, and that one was, we were pushing the limits on that. And I turned around to the client and advised them, get a Cat 3 check. I need a sense check on this because we've got too many different forms of construction, too many low balancing, this, that, the other, too many moving parts. I need a fresh pair of eyes on that. And so they did. So yeah, it's predominantly with the client, but I think that needs to know, I think we need to be asking that question. If we're bringing the limit down from 15 to 7, does that trigger Cat 3 checks within the industry? And then especially, do you have the competence to do that Cat 3 checking? Who's checking my work, for instance?
Yeah, it's interesting. And as we were talking about last night, we don't have that as such in fire. So we have peer reviewing, but not mandatory. And it's often led by, Andrea's just made the point, actually, if an engineer is at the extent of their competency, I might think, well, I want someone else to check this. Or client led, we want a second pair of eyes on this just to double check because it's a huge investment or approvals risk or whatever it is. So not a mandatory check. A point on fire that we didn't discuss too much last night about this categorization of buildings. We don't have that equivalency in fire. So in fire engineering, we would have a purpose group or a risk profile, which is a kind of broader description of what that building is. So you could have a purpose group of assembly and recreation, like a university building, but that could be 1 story or it could be 25 stories. And what you're looking at is, actually, if we go to 9999, we do a risk profile, which is an assessment of 2 things. The type of person in the building. So are they awake and familiar, awake and unfamiliar with the building? And what's the fire risk, the growth rate of any materials in that building? But again, that's not directly proportionate to height of the building. It's not necessarily a trigger height. We do have trigger heights for sprinklers over 11, firefighting shafts over 18, etc., etc. But in terms of broadly classifying buildings, we don't until we now have the HRB classification that we have as that standard 7 stories or more. So it doesn't align in terms of that classification. There is no, in terms of fire, I always give this example that a 1-story care home is higher risk than a 4-story student resi. You can have different proportionate risk, and it's not only proportionate to the height of the building. And that's the example that I always give. Go on, sorry.
I was just thinking that when you were talking about your different, you don't have it. We have 5 different categories. So 3 are the main ones that we use. 4 is basically national infrastructure. If that fails, it makes national news. Bridge failure, Grenfell, for instance, they're all Cat 4. Then Cat 5 is like a big nuclear plant. It affects everybody around it. Off you go. Obviously, that's all big civil work. Don't work with that. But I'm just wondering, I think this category of classification needs to come in on the risk assessments, because then you understand the consequence of your actions. So like your example then, the difference between a care home and a 25-story building, they probably would fall under different consequence classes. Because that definitely, we'd be looking at it like that anyway. So it'd be useful if you guys looked at that similar to us as well in that sense.
It's an interesting element. I mean, what we could have is 2 areas of the same building with very, very different design behavioral scenarios. So you could have I use, again, in my teaching, I have an example where if you have a front of house in a shop, you typically have occupants who are awakened unfamiliar because they've never been there before, but a lower category of fire hazard because there's less stock. And in the back of house, you've got the inverse of that. You've got everybody's familiar because they're back of house, but you have more stock, so a higher fire risk. So the risk in terms of combustibility versus the risk of the occupants themselves. And then we have a third one technically, which is the risk of the wider building environment. So we do this on a kind of wider sense, but it isn't categorized broadly because you could be at higher risk in a basement than you are on the 10th floor if that basement is not ventilated and the fire risk is greater and you're unfamiliar. So yeah, it's not quite as clear in fire, but I suppose we do broadly categorize parts of buildings in a similar way. But going back to the original question, we don't have Cat 3 checking as a mandatory thing. We do that ourselves if we're at the limit of competency. I suppose internal within companies, I'm always saying to my guys, can you double check a pair of eyes on this? So we have that competency in terms of ethics within the industry, but then often client led on big schemes or where we've got, actually one thing I've seen that's quite positive, I've been looking at the names, I don't know if we've got any building control approved inspectors or BSR on the call, but increasingly we get a building control officer approved inspector say, I want a pair of eyes on this that has equivalent competency to the engineer. So you've got the person signing it off and marking it or checking it. That is that secondary peer review, but not as a mandatory check as you guys have. So no, I suppose is the answer. Good to clarify that a bit. Okay, cool. I've got another couple of questions I'll get in before the 10 o'clock if that's good.
Yeah.
One from me actually that I wrote down as you were talking. Okay, about I liked what you said, and I think it's interesting about giving information to residents, but also not terrifying them with technical content. So the day, I must have told you this story, but the day that Grenfell happened, I went to the tower because I lived quite nearby, and I lived in a 10-story building on the 10th floor, over on the other side of London, but still kind of living in a building that I felt was at risk. And I emailed the landlord or managing agent and said, can you send me some information about fire in my own building? Not letting them know that I work in fire. And they said no. They said we don't share that information. And then over the years, that's now become a mandatory requirement. But had I received the information from the building manager then, I would have been immediately terrified because there was lots of risks in the building that I could see because I knew what I was looking for. And if an unknowing person, somebody without competency or skills gets that and suddenly finds out there's a risk of disproportionate collapse, it is, you used the word, I wrote it down, widespread panic. So how would you communicate that? Or how would you like to see it communicated, I suppose, in terms of the point you made about your building hasn't changed, but the regs have. The guys that live in the building don't know the regs. So how is it communicated? Or what do you think it could be communicated?
Been thinking about this quite a while, for obvious reasons. And yeah, I think the changing the regs, not changing the building, is the easiest one at the minute, and trying to push additional safety measures coming into the building so that everybody will know Grenfell. And we can explain, okay, post Grenfell, these are the laws that have come in. This is what's changed the industry. This is now why you're going to start seeing different consultants around the building. This is why we're doing risk assessments in the building. We're identifying any weak spots and then we're going to patch them. This is the requirements. This is the additional safety. So if anything, you should be seeing, I don't know, sprinklers going in, maybe a second stair core. We might be doing additional work structurally to the building here and there. This is why. It's not, and then enhancing the safety or something like that. I think you need to be considerate and careful with how you word it. I haven't got the answers on this, and we're still kind of like drafting a few stuff at the minute, but fully aware that we could cause panic at the minute. I just think it needs to be carefully done.
I mean, I go through the same thing where if somebody just receives a 60-page fire strategy or a fire risk assessment, you look to the bits that identify hazards or identify derogations, and that immediately becomes widespread panic, as you say, and more so particularly with structures. So yeah, it's how that's communicated is a big issue. I think for the first one, the one client we spoke to, we were talking on our last session with them that they were just gearing up all their communication with the residents and getting all that right. And then the lady in charge of communications, she was like visibly almost kind of panicking. She was like, but I don't know about this. I'm going, look, if I need to be on that call or that first video call or a first anything to the residents, I can field those questions. Like, it's easier for me than for you to sit here, take 100 questions, everybody goes off worse, feeling worse. It's no, here are the professionals, this is what we're saying, this is what we're doing, and off you go. I think that will help a lot as well. And at least they can put a face to the name, even if all the questions still get directed back to the client and their process that they've got through.
we can at least explain, like, this is what we're doing and why we're doing it. Just rather than, no, not my responsibility. No, don't care. No, I'm going to answer those on Friday. These are people's lives. We are kind of like messing about with, especially in existing buildings. So I think we need to be very careful of that.
Absolutely. Okay, brilliant. Thank you, Sean. There's some more stuff in the chat we can scroll through and go through throughout the session, but we'll take a couple of minutes before the next session. So thanks for running through the competency stuff. I think if it works, the next session I think is mine, isn't it, with the introduction to fire engineering. So for anyone on the call wondering kind of what the next couple of sessions are, as part of the competency stuff Sean has been talking about, there is this obligation to understand other disciplines at quite a high level, not to be experts in it, but know a bit about. So Sean and I have both written an introduction to our respective disciplines under the, or in the spirit of, there are no stupid questions. So for fire engineers listening to mine, it is very much day one fire engineering. But when day one structural engineering comes in, really, really useful stuff. I went through Sean's slides this morning for structures, and there's stuff in there that I've been wanting to ask a structural engineer for quite some time. So the next couple of sessions are these introductions. I'm going to do introduction to fire engineering starting in 3 or 4 minutes. And then Sean, I think it's lunch, isn't it? Or we're taking a break and then back on with you again from 11ish.
Yeah, we'll run through till 11, quick break, 11 to 11:15, and then I'll keep an eye on the chat and everything through here as well. But obviously I'm interested in this. I want to listen to this as well. So I'll try my best to keep up with the questions, keep an eye on that as well. And then there's a couple of minutes here. I'm just going to run through the questions from here as well and just see what else is there, and I'll try to reply where I can.
Fantastic. Well, what I'll do now is I'll load up my slides. I'll get them up on the screen. Let's see if I share my screen. I'll lose the chat at that point, but thank you again to everyone for going through the showing some things in the chat. So hopefully, Sean, you've got high risk buildings front page there. Is that looking okay?
Yeah, you're all good.
Jolly good. I'll give it a few seconds and then I'll go through. Somebody has just texted me and asked if there's a sword in the background of my camera. The answer to that one is yes. I've recently moved house and I've unpacked in a weird order, so I'm kind of sat in an empty office in the loft, just with a sword. So yes, thank you to actually the 2 people who've texted me and asked me that. Hopefully the easiest question I get today. No, hopefully the hardest question I get today. But we'll see how we get on with this. So, right, let me launch in. So, as Sean alluded to at the beginning, Sean and I first met through kind of working in our respective industries and having an appreciation of each other's. I'll tell you a bit about my background on the next slide for those of us that don't know each other. But one thing that we have in common, Sean and I, is this kind of passion for learning and CPD. Sean probably is the only person I know who reads more than I do and is kind of obsessed with this idea of learning, which is why perhaps we're such close friends. And one thing we're particularly passionate about is sharing information between disciplines. And reading the Building Safety Act and all of the secondary legislation, it's impossible to ignore that idea that we now have to understand more about each other's. Particularly of note was your point you made about structures having additional points and having to understand fire. So for anyone on the call who works in a certain discipline, I encourage us now to kind of open up and think about the other disciplines. I've been an engineer for a good few years, about 10, 12 years practicing as a fire engineer. And over the previous years, there's always been this, not by myself, but I've always heard of this, it's not my job, ask the structures person or ask the mechanical engineer. And that's disappearing these days. I think there's an obligation to understand a bit more. So the next few slides, I've got about 20 slides on this. I'll go about 40 minutes, hopefully. Is an introduction to fire engineering. It really is the highest level that we can do. And I hope it gives you guys who don't work in fire engineering a bit of an understanding of who we are and what we do. So my name's Joe Hart. I'm the Group Director and Founder of the Delta Innovation Group. I stole this from your slide, Sean. I crossed out structures and wrote fire, but that's very much what I want to be the ethos of these next 2 sessions. If there's anything you've always wondered about fire engineering, now is the time to ask. I'm here. We've got a bunch of fire engineers on the call in the chat, and we can go through and hopefully answer some of those. So in terms of myself and who I am, why I'm sort of here, I split my time between multiple roles. I sort of collect job titles at the moment. I have half a foot in academia, or 1 foot in academia, and 1 foot commercially as well. So 2 years ago, I founded the Delta Innovation Group, which is a series of fire safety companies, starting with Delta Fire Engineering, which I'm still head of fire engineering at, working actively on about 18 or 20 projects at the moment of my own, and overseeing my team of engineers. We've got 9 engineers now working across the UK. I'm also head of R&D at Delta Research and Development. We invest basically all the money we make after we pay our costs into R&D, so we can give back to industry and do loads of things that we think are really important. And also Delta Fire Training, which is our newest business, where we deliver training courses, not dissimilar to this, but we do that for clients and also for commercial partners. And I also found another group, so the Delta Compliance Group. I've got another 2 businesses there, Delta Fire Safety, who do fire risk assessments and compartmentation surveys, and also a construction firm called Delta Fire Protection. So we install passive fire. So I oversee everything that happens at Delta. Principally, I'm involved as head of R&D at Research and Development and head of fire engineering. And alongside all of that, I'm also a lecturer. So some of us on the call, quite a few of us on the call actually, know each other from the university. I teach fire engineering, so I wrote big chunks of the course related to the industry. I took that job kind of in the spirit of everything we're talking about today. I felt like I wanted to give back to people in early careers and what they are going to learn and what they need to know, and try and front end some of their work. So anyone who's been through my program at the university, I teach fire safety law, fire engineering design, fire protection engineering, advanced projects, stuff like that, is all about what we're going to talk about hopefully throughout today. So I put my contact details on there. Please do reach out if you want to chat afterwards. Lots of us know each other anyway, but it's always good to meet more folks from doing things like this. So, right, I'll get into it. So an introduction to what fire engineering is. I would very much call this Fire Engineering 101. And I'm going to start, as I always do when I teach this, with the sort of history of fire and how we get to where we currently are. And I do this slide more than any slide of any presentation that I do. I have thousands of slides, I have hundreds of hours of CPD, and this starts most of them. That fire engineering really is a multidisciplinary field. In fire engineering, designing buildings, designing the built environment, we have to consider lots of different elements. We have the principal sciences in everything that we do. So chemistry at the top, the chemistry of fire and combustion. Fire itself is a chemical reaction. Biology, we're interested in the effect on humans and animals within buildings. And physics, the way that things physically travel around. Fluid dynamics being a big one, fire and smoke and how they travel around a building. And in amongst all of fire engineering, we also have to do everything else. Risk assessment, we're going to talk a little bit about today. That's a big part of our fire strategy designs. Structural engineering, one of our functional requirements that we'll discuss is on structural fire resistance. How do we protect elements of structure? Quantity surveying, mechanical engineering, architecture, things that are common to structures and fire, but we have to understand these ancillary disciplines. Mathematics, fire engineering is a very technical field when it's done correctly, and project management, again, similar to us. So I start with this slide and I often come back to it and say, the first thing when I'm talking about fire is that it is a merge of multiple different disciplines and fields. So I suppose it's also history, because we go back a few hundred years now. On the next couple of slides, I want to highlight an element of fire that's really important to understand, and it's the development of fire over time. And I don't mean the physical characteristics of fire. I mean us as an industry and the practice of designing fire. And when I teach, one of the first module I teach on the degree program is called Fire Safety Law, and it's a first-year module, and we learn all about legislation and guidance and where it comes from. And I start with the history of, and I do these slides, and I present what I call my 18-month rule. It takes roughly 18 months for a piece of legislation to be drafted, to go from a green or white paper right up to royal assent. And if you take any piece of fire legislation, go back 18 months and you'll find the fire, generally speaking. And it's the same in any safety or health and safety legislation. So much of what we do is influenced by previous incidents and previous fires, in our case, that have occurred. And one notable thing that we'll pick out, and I'm going to come to the Building Safety Act on this, of course, but one thing that we pick out is the things that are legislated or written into our guidance, if you do a root cause analysis on the incident, is often what's legislated out. Or in more simple terms, something goes wrong, we realise what that thing was, and we try to prevent it happening again. And we see this throughout history. So if I go right the way back, and this isn't a law lecture, these are just a few slides to set us up for where we're at currently. If we go back to 1667, we had the Rebuilding the City of London Act, and in there it banned certain things. It said you must space buildings a certain separation distance apart. We still have that regulation, Regulation B4. There was a limitation on storage of explosives in the home, because this was a few years after the English Civil War, so there was a high incidence of explosives being stored. And timber buildings were banned over a certain height. And if you take, in this case, they were a bit quicker in the 17th century at drafting legislation. Go back 6 months and you get the Great Fire of London. And you can draw the parallels between these two things. The Great Fire of London itself was a mass conflagration, an urban conflagration, so a fire that spread between multiple premises. In fact, it destroyed 3/4 of the ancient city. It spread rapidly between tightly packed buildings that were constructed of timber. So 6 months later, in this case, we get a piece of legislation that says, okay, because that was an issue, we identify that now as being a root cause. We legislate that out. The Rebuilding the City of London Act says we can no longer do that. And fast forward to more modern times, some of us remember these incidents I'm going to talk about next. We see exactly the same again. If we go back to 1989, we get the subsurface regulations. They apply to subsurface railway stations. And in fact, any tunnel that's open to the public, even pedestrian tunnels, interestingly. We have a requirement to put sprinklers in, which is not something we would have done typically, because sprinklers in underground areas are difficult in terms of pumping water out post-incident and the potential runoffs. A duty to manage means of escape and firefighting facilities in these environments, and surface linings particularly legislated under secondary legislation that they must meet a certain standard. And again, if we apply my 18-month rule, we go back and we get the King's Cross fire of 1987. Now, I talk about root cause analysis, and I teach that a lot at the university. If you look at the things that are legislated and you look at the incident, you find a direct parallel. So in the King's Cross fire, again, I'm not presenting this as a case study, it's just to highlight a point. It was the surface linings that contributed particularly to flashover occurring in the ticket hall. These are photographs from the actual incident. So you can see that the surface linings had contributed in terms of propagation along the surface and also combustion of those elements as well. Even the posters in the top right image had ignited. The King's Cross fire itself resulted in 31 fatalities. What we often find is an incident that has a high proportion of fatalities, injuries, or undue loss of property or business or operational continuity. We'll get some investigation into it and often find that we change our rules or guidance. Another example, I think slightly earlier, the Places of Safety of Sport Act 1987. So this brought in an obligation. I was actually teaching a course on this yesterday afternoon at the university. So we had a duty to assess means of escape and provision of sports premises. Specifically, what it brings in is a requirement, a legal duty to manage sporting events during the event, not just in the design of the stadia. So a regulation that says once we've designed it and it's occupied, we have to manage it in a particular way. And again, with our 18-month rule, we go back and we find a really significant fire. I live not far from Bradford, up in North Yorkshire. And this fire still resonates sort of in the community and people that were there on the day and with people living in and around the area. If anyone's not familiar with this fire, I encourage you to look into it. Certainly fire engineers, we should all be familiar with the Bradford City fire. It was a fire that occurred in the stand. Really notable, though, is that it was a football match being played, and we have the footage from the cameras that were filming the match. The YouTube link is there. In fact, you can watch it. Really significant fire that came about. And when you look at the fatalities, 56 fatalities in this case, a large proportion of them were as a result of the management during the game rather than the design. What actually happened, and if you read the report into it, a major contributory factor to the number of fatalities was the locking of turnstiles at half-time or after the game had started, because there was an issue with people coming in without tickets. So the duty for management is something I talk about a lot throughout today, as well as duty of design. And again, this fits with our sort of 18-month rule from incident through to legislation or guidance. The last point on this before I come to where we are currently in industry in terms of fire. We see this also in fire. We look retrospectively at data over time, statistics over time. It's a very analytical field, I find. Certainly when we're writing guidance and writing legislation, we look for major incidents and trends. And anyone who's seen my lectures before will be familiar with these next couple of slides, but it's an example I like because it highlights the point really well. And it brings in some of our instances of fire, so some of our risk that we're looking at. If we look at the graph on screen, we've got the number of fatalities in fires from 1981 up to almost the present day, 2020. And this graph shows the proportion of fatalities in dwelling fires versus other fires, and the Grenfell Tower fire is in there as a standalone data point as well. But what we see, and I'm not a data analyst, I do this for the purposes of engineering, but to my untrained eye, I can see that the graph is going down. So from 1981, we had around 750 fatalities per year, and up to almost the present day, what are we, 250. So we've reduced down there to a third of where it was. And this is the sort of data that's used in the drafting of our guidance and legislation and in our risk-based approaches to say, well, this is a positive trend. We've seen a decrease, whilst interestingly saying that the proportion of dwelling fire fatalities is broadly the same across. You would say perhaps 80%, 85% of fatalities occur in dwellings rather than other fires, but generally a downward trend. And Related into this as well is things to do with funding for fire services and funding for general fire precautions work, and whether we need to draft guidance, etc., etc. So you look at this and see a positive trend. But over time, this is a slightly wider version of the same graph. You see 1981, we had 750 fatalities, slightly more in here because it goes beyond the fire, so forget about the blue at the top. You see that actually that 1981 statistic was just the top of a bell curve. And actually from the 1950s up to the 1980s, there had been this huge increase in fatalities in the UK. And it's this sort of work that's really intrinsic to fire. When we're talking not just about designing a school or writing a fire strategy or doing something, but on the wider perspective, which is where we're working here in the Building Safety Act, we're looking at wider trends in fire engineering. It's where I spend a lot of my time. We look at the wider industry, and it's this sort of analysis that's really useful. If we look at what's happened from 1981 to 2020-ish, slightly different data set, downward trend. But actually there is just an upward trend from the 1950s. And this is a really interesting area of fire safety for me, this analysis of how effective we're being. Because what happened in the 1950s, we know why this happened. If we look at the colour bars, we can see, again, proportions of the data. So the burns didn't really change. So fatalities as a result of direct heat exposure. But what's driving the trend is overcome by gas, smoke and toxic fumes. It was toxicity that was driving this increase in fatalities from 1950s up to 1980s. And when I teach this in the classroom, I say, does anyone know what this is? And I can't do that today, but generally this is quite well accepted and understood within fire, not so much outside of, but it is an interesting little statistic. What it was that was driving this change in fatalities was, in fact, the types of materials we had in buildings, internal to buildings, not in the structure itself. So from the 1950s onwards, we started to use more synthetic materials, foam, mattresses, polyurethane, different materials we were putting into people's homes. And that drove over a 30-year period or 25-year period, a huge increase in toxicity. And what we did, bringing it to where we are now in terms of legislation and guidance, is in 1980, this was identified and we started to test upholstered furniture. We brought in the upholstered furniture safety regulations. If you go now to get rid of a sofa at a charity shop, you can't do it without one of those labels on it. You have to demonstrate it's been tested to the standards that were brought in as a result of that wider industry change. So nowadays we put fire labels on things to say that post 1980 we've tested it accordingly, and if we can't demonstrate we have that, it can't be used in buildings or we can't market that product. And again, just an interesting statistic to pull out, we actually have an updated version in 1988 of that particular regulation. And if you read it, it says there is a specific exemption for something that's pre-1950, which is the date at which we saw this increase in toxicity occur. So that's a bit of a brief run through to start with some history of fire. The key salient point I want to do there, before I come on to the other one, the next one, is that fire safety is beyond what we see in buildings. It's not simply the kind of detector you see in your home or the extinguisher you see when you go down the pub or you walk into a shop and you see a fire exit sign. There are wider kind of industry trends that we look at and also wider consequences of real incidents. We spend a lot of time, certainly I spend a lot of time reading into case studies, looking at fires that are happening now when they make the news. I research in a lot of detail if I can. I look into the design of the building and what perhaps led to it, and also historic. There's a huge element of our industry that is looking historically at what's occurred. And where we get to today, of course, we've looked at the competency already with Sean this morning. Throughout today, we're going to get a little bit more. The Building Safety Act is no different. We know, hopefully, the Building Safety Act has come in following the fire at Grenfell Tower. It was enacted, and now all the secondary legislation we have and continue to get is as a direct result of that incident and the trends that have occurred over time. That trend doesn't have to be plotted on a graph. It can be anecdotal, cultural shifts. Everything we've seen in the industry over the past, well, decades, frankly, is now seeking to be undone by the Building Safety Act and change the regimes that we have. The Building Safety Act itself is changing the way that buildings are designed, reviewed and managed for fire safety. It's a really interesting point. It's not simply the design. There was a question this morning that I didn't quite get to about, are we looking at the design of buildings or existing buildings? And one thing with the Building Safety Act is it transcends both. It has changed the regime we have both for new builds and also existing buildings that we're reviewing. Other things it has done is establish the building safety regulator, changed our regulatory regime. And I suppose one of the salient points we've touched on so far is that it has sharpened focus on competency. So those working in fire safety, the Hackett review, when we read, and the raising the bar reports and setting the bar reports, very, very much focused on who's making decisions, what are their competency, who should be making decisions, and how do we document all those things with the golden thread of information. So one other focus, and this is why Sean and I are here doing this. Really, the reason we're doing this and the reason it's free and we're giving it out to everyone is this is Sean and I swapping notes. But we think that the fact we need to swap notes, being in the positions that we're at, suggests other people want to do the same as well. And it's great that so many people have dialed in to do the same. This is a note swap exercise. This is just us sharing what we know so we can all learn from each other. Because particular focus, post-Building Safety Act and post-Grenfell certainly, is about learning from other disciplines and sharing what we know and learning from everyone else around, collaborating on projects and collaborating in wider industry. So to come on to what we actually do then in terms of fire engineering, this is just finalising the point there about the history of regs. So legislation is often influenced by our historic events. That's not unique to fire. It's so prevalent in fire though. Go back 18 months from the regulation and find the fire. It's a game that you can play. It holds so well with everything that we find. Any incident unprecedented in terms of scale, damage or loss of life will often draw scrutiny of the regulations. How was it that this thing was allowed to be constructed? How was it that people were put at that undue risk, and why did that incident occur? Will often bring in change legislation. So bringing us to where we are, I wrote these slides after having read Sean's, and I quite liked the way that it was presented, simply going through what we do day to day that I take for granted in terms of what rules am I bound by and what do I look at when I'm designing those particular buildings. So we are familiar, I presume, with the building regulations, the vast majority of us. Perhaps not, though. I know I've got some folks dialed in who want to learn about fire engineering who work in other fire industries. There's a point I want to make very briefly that actually I've very recently, in fact, stopped calling it the fire industry, because something that I've learned now that I'm in my position holding multiple roles, I've realized that actually I work in lots of different fire industries. I work in the fire engineering industry, academic, which is itself an industry, but I'm also in the fire risk assessment industry, the fire construction industry. Each of those are very different. They operate in different ways. And I've only really realized that literally in the last 6 weeks. I've had a bit of a light bulb moment that I now refer to the fire sector. So within the fire sector, we have all of these disciplines working together and multiple industries. The fire engineering industry here, we're looking principally at our building regulations. So in terms of functional requirements, we have 5. Part B. Part A, of course, is you guys over in structure. We're Part B. We're right on your coattails in Schedule 1. We have 5 functional requirements, and they work the exact same as any of the rest of our functional building regs. It doesn't tell us exactly what we need to do. It gives us a function. It gives us a definition of what we need to achieve, and it's for us to design. There is a slight difference we have now with Regulation 7, of course. We now have a legal duty for cladding of high-rise buildings. But broadly, for what we're talking about at this stage for an introduction, it is the functional requirements B1 through B5. Each one of these covers a different element of fire strategy design, designed for fire safety in buildings, starting with B1, means of warning and escape, which says we must have reasonable facilities or adequate facilities, I think it says. It is on the next slide, so we'll come back to it. For means of warning and escape of occupants in buildings, so we must be able to alert people to a fire and ensure they can escape unaided without the assistance of the fire service. B2 regulation B2, internal fire spread linings, limits materials we can put on every material that you see as you stand in a room and look at it for walls and ceilings. Doesn't apply to floors, interestingly. But it is the exposed surface and the contribution of that material to a growing fire. B3, internal fire spread structure. I'm going to come back to that this afternoon in a bit more detail than I'll do in the next few slides, because I really want to touch on a point there about how we define what we call periods of fire resistance. So is it 30 minutes? Is it 60? Is it 90? Essentially, our duty is to ensure that we've got an appropriate standard to the structure of the building, but also that we've subdivided that building internally with periods of fire resistance. So we break down with compartments, we separate flats from one another, we separate means of escape, protect stairs, etc., etc. External fire spread, so that's separation between buildings, ensuring that if building 1 is on fire, building 2 is protected, and also that we don't have undue spread on the outside face of a building via the wall or the roof that could breach our internal compartmentation. If we go to all the effort of putting fire doors and compartment walls inside a building, but the fire can spread over the external face and breach compartmentation, it undermines completely the strategy that we're aiming to achieve. And B5, access facilities for the fire service. We have a legal duty under Regulation B5 to provide suitable access to sites and around sites. as well as facilities internal to the building. So whether that's dry risers, wet risers, smoke control systems, all those things for the fire service. I'm going to come back onto each of these in turn. That's just a brief introduction. But broadly, in terms of fire strategy and fire engineering, we are always coming back to our 5 functional requirements. As in structure, we go to our 3 functional requirements under Part A. The sorts of things that we'd be looking at in these, that looks a bit blurry, that, doesn't it? That's a shame. But that is our functional requirement. That is B1. That one sentence there is what we have to do to protect people in buildings and make sure they're alerted to a fire. I always highlight the functional component of the functional requirement when I teach these slides. It simply says the building shall be designed and constructed so there are appropriate provisions for the early warning of fire and appropriate means of escape in the case of fire to a place of safety. It doesn't tell us what is appropriate. It doesn't say that you must have a fire alarm system. It doesn't say, here's a can of worms for everyone. It doesn't say you must have 2 stairs in a building. Let's move on from that comment before I get too much backlash. It simply says it must be appropriate, and it is inferred that that's appropriate to the risk of the building. Things that we might be putting into the building, starting with fire alarm and detection systems, very familiar to each of us. Probably if we go into a building, interesting because I moved into this house so recently, I don't actually have a smoke detector in the loft. There's just a hole on the ceiling where it should be. But familiar to us as we walk around, we would see fire alarm detection systems. We know, of course, as being competent people on this call, that they do lots of different things other than just alerting occupants. They're interfaced with different systems. Our fire alarm or our fire detectors may well interface with a smoke control, may well interface with a red care unit that alerts the fire service. It extends slightly beyond just beep, 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 there's a fire in the building. But if that's what's deemed to be appropriate, that is what we put in under Regulation B1. Moving on from the means of warning, we have means of escape. So horizontal and vertical means of escape. We always break down the means of escape for occupants into those 2 components. First of all, we travel on the floor of pedestrian origin. So that would be me going to the stair over in the back corner of the room and then traveling vertically down the building. We have to design for each of these things to determine what's appropriate. How quickly should we get people out of the building? Should we subdivide the building so that you reach a place of safety sooner in your travel? Or do we design for people to evacuate entirely? If it's a hospital, is it appropriate for us to design for people to evacuate directly to outside? I recently peer reviewed, talking about peer review earlier, a care home, a dementia care home, where the means of escape strategy that had been designed was to evacuate to the car park. And residents would go out to the car park and they would simply stand there and wait until the fire service arrived. And I peer reviewed it and said that is completely, well, I literally used the word inappropriate. It didn't meet functional requirement B1 for me because it wasn't appropriate means of escape. We have guidance around these. Of course, I'm going to talk this afternoon a little bit about prescriptive, risk-based and performance-based, similar to you did this morning, Sean. But essentially, we are designing this to the functional requirement of what is appropriate. Other things we would put in: travel distance and travel time to evacuate a building, fire safety signage, where that might be located, emergency lighting, and protection of escape routes. Do we have fire-rated doors and walls, fire-rated glazing, smoke control? All those kind of things comes principally under requirement B1, means of warning and escape. Continuing through these, they get slightly longer, the functional requirements, but still only a couple of sentences here. We have the legal requirement or legal duty to limit combustibility and reaction to fire of materials interior to the building. What it says, it's in 2 parts, this one. It says to inhibit the spread of fire within the building, the internal lining shall adequately resist the spread of flame over their surfaces, and if ignited, have a rate of heat release or fire growth which is reasonable in the circumstances. Again, it doesn't say that if a fire starts in the corner of a room, it shouldn't spread 3 meters laterally. It doesn't say it shouldn't spread to the ceiling. It simply says material should adequately resist. And again, this is related to risk. The larger the room, the different the classification there is, the use of the space, the different internal lining classification. We might say in a means of escape, we want to have a higher category. We might have a class A or class B material, as opposed to a class C that would be permitted in a small storeroom that's ancillary to the use of the wider building. Essentially, what we're going for here is the materials that are exposed to a fire once that fire grows. If we go for kind of elementary or principal fire dynamics, if a fire starts in a room, it spreads to, it forms an upper layer. We get the ceiling, it becomes the upper boundary of the fire. That's our hot layer, and it begins to descend. And if we get ignition of the internal linings, that fire is spreading, and we get the risk then of flashover. We get the risk of uncontrolled fire spread in that environment. And the way we seek to mitigate that is with a restriction on what those internal linings are, because if they're exposed, as we look at them in the building, it's inferred they're also exposed to the growing fire as well. So this relates to the reaction to fire properties, the combustibility properties of the materials interior to a building. That's another legal requirement for us. Coming on to our most extensive of the functional requirements, regulation B3. So internal fire spread structure. A period of fire resistance should be assigned. It said that the building, or it says the building should be designed and constructed so that its stability is maintained, quote, for a reasonable period. It's not defined in that in the regulation, at least. Reasonable period is up to the designer to decide, and that's the talk I'm going to give this afternoon about how we determine that, and really sort of one of the issues we have with that about design fires. So that's our principal requirement under regulation B3. We also have to subdivide the building, as I mentioned earlier. So we have to have walls common to 2 or more buildings, or actually 2 or more tenants. 2 or more uses within the building should adequately resist the spread of fire between those buildings. And also we should subdivide the building to an extent appropriate to the size and intended use of. Again, the risk in the building is an important factor here. We break the building up to try and limit fire spread. The final point on there as well is we subdivide cavities and void spaces to prevent or restrict smoke and flame spread throughout the building. So under our legal duty here, it's multifaceted. First of all, for B3, we have to ensure the building will remain structurally sound for a period of, or for a reasonable period. We subdivide the building using elements of structure and passive fire protection within the building. Could be active, but generally solid partitions to break up the fire, restrict its growth and protect certain areas of the building. And we subdivide areas that we can't see, fire and smoke, to make sure that it doesn't spread again beyond the area that we want to limit the fire to. Requirement B4, external fire spread, perhaps the one that has been discussed the most at length over the last few years. We have a number of requirements under B4. It's down as 2 there, but within each of those, we actually have 2 requirements for each as well. First of all, we have space separation. So we space buildings appropriately to ensure that if we have a fire in building 1, it doesn't spread to building 2, or at least we limit the likelihood that it will. What we seek to do is to put buildings sufficiently far apart from one another so that the risk of fire spread is limited. Or if we can't do that, we have to protect the external face of the building. So one of the calculations we would do under a fire strategy is to look at the risk of fire spread between 2 buildings and mitigate that by moving the buildings further apart. Easier to do for a new build, much harder to do for existing buildings. Or we'd fire protect some of the external facade and create a radiation shield. We would put something in there to prevent fire spreading from building 1 to building 2. Big part of external fire spread from requirement B4. But another component of that is what I mentioned earlier, which is a fire breaching compartmentation via the outside face. We don't have to think back too far. We probably don't have to work hard to bring to mind the pictures of Grenfell, where the fire spread over the external wall. So that, in terms of performance requirement B4, is something that we're looking at, where we're trying to adequately resist, I'm back to the image on screen there, adequately resist the spread of fire over the walls as well as from one building to another. And again, having regard to the height, use and position of the building, to the risk we've got in that building, we have to have different standards and classification. And one point I want to make on this, because I want to highlight the complexity we have in each of these functional requirements. As you drill down into them, as I spend a lot of time doing, they get more and more complex. When we consider external fire spread, there are 3 mechanisms by which we might get fire spread between 2 buildings. The first one is by direct flame impingement. So we might get a flame that breaks out from a building, physically impinges on another structure, touches that building, and it spreads through direct flame touching or direct flame impingement. Secondly, it might be through radiation. So radiation that's emitted from a building, we will calculate the amount of radiation from the compartment once the windows break and the external wall fails, how much radiation comes out, and at a given distance, what's the likelihood we would ignite building 2. And the third one is something we sort of can't design against. It's burning brands that come from buildings. So if we have a small component of the building, small fuel source, and it breaks away from the main building, and if you've been to fires, any firefighters on the call, or anybody who has seen a fire or even seen videos, particularly wildfires is where we get this an awful lot. You get parts of the fire breaking away and being carried by wind or convection. So the fire itself gives out convection currents and forces these things to travel. And that's why we also look at the roof of the building. Now, the roof of the building itself is an intrinsic part of the structure, so we're interested in it anyway. But one of the principal means of fire spread externally between buildings are brands that are given off from the fire and land on adjacent roofs. So we protect the roof in a number of different ways, and this is a big component of a fire strategy, often overlooked. That's just anecdotal, but I see that this is something that's often forgotten about, that the risk of fire on a roof is twofold. First of all, it's a fire breaking out from the building, spreading over the roof and breaking back in. But secondly, it's an external fire source hitting the roof and breaking down into the building as well. Multifaceted, the external fire spread for both walls and roofs. Big part of any fire strategy we're looking at, certainly these days. And then finally, performance requirement B5. So the access and the facilities for the fire service. We have the legal duty, we have the functional requirement in two parts again. The building should be designed and constructed to provide reasonable facilities to assist firefighters, in the protection of life. And reasonable provision should be made within the site of the building to enable fire appliances to gain access. So things we might be putting into a building, we would be looking at access to the building. We look at the access roads. What's the width of those roads? Can you get a fire appliance down there? If you're driving a fire appliance down, is it just a typical fire tender? Is it a water carrier? Is it a high reach appliance? Is it a special appliance? Is it just a pump? Is there sufficient holding capacity, weighting capacity for multiple appliances? If we had a multiple make pumps 10, we've got 10 fire appliances on site, is there sufficient space for them to be? Do we have access beyond where the building site is, but where's the nearest fire hydrant? Is it within 90 meters of the site? Do we have access to water? We look far beyond the building itself when we consider regulation B5. As well as the reasonable facilities once we've accessed sites, so we're writing the operational firefighting strategy to say once we get up to the building, what do we do once we get there? Do we commit firefighters to the building? We always design on the basis of we've put sufficient things in place that we could effect firefighting operations, because what we're doing under B5 Part 1 is providing reasonable facilities to assist firefighters. So what we're aiming to do is ensure there are facilities internal to the building as well as external. It might be we're putting in dry risers within the stair, or even a wet riser if needed, which allows us to get water on the fire without dragging hose across the every landing and up the stair. Consideration for operational firefighting. Where would the operational firefighters establish a bridgehead, as we would call it? Where would they physically set up in the building? Would it be on the floor of the fire? Would it be the floor below? What's the reasonable facility in which they would do that? I'm actually, at the moment, I've been working on this for a couple of years, and we're going to do it very soon. I had a meeting about it last week, in fact. All of my engineering students, I want to do some firefighting as part of their course. I think anybody who designs section B5 of a fire strategy should have carried a hose over 45 meters, should have walked in fire kit up a flight of stairs. And at the university, we're fortunate to have some facilities to do that. We teach both operational firefighting as a degree and fire engineering. I simply sort of put them together and said, why don't you guys work from each other? Big thing I'm doing at the moment with disciplines and different areas. And we're working on that. And again, we're opening that out to industry through some of the work at Delta, where we want to give access to fire service, I suppose access to the knowledge of the fire service to engineers and designers, and vice versa as well. So we've got some things we're filming at the moment for that, which are really interesting, because it's very easy to write it on a page, and if you've not done it yourself, it's very difficult. I'm fortunate enough to have done it myself quite early in my career, to have done some training in actually fighting fires. Great experience, big part of us for our fire strategies. And then the final point on there about provision for the fire service to enter and move around site. Again, if we drive a fire appliance onto a site, do we have turning provision? Can that fire appliance reverse, turn around in a hammerhead, otherwise have a turning circle? If they need to, they can withdraw from the building and perhaps bring in another fire appliance or whatever it is they choose to do operationally. So B5, access facilities for the fire service, is one of our big considerations. All of these, if I skim back, I'm going to take the opportunity to just go back to them super quick and highlight them again. Huge consideration both in existing and new builds. So in a new build, we have guidance for each of these things. We have our British standards, as we'd have in any discipline, that tell us minimum category of alarm, how far apart detectors should be. Similarly, for internal fire spread linings, we've got guidance on what type of room, the risk of that room, and what we should be building in. We can calculate the required element of structure, period of fire resistance, based on the reasonable worst case fire size. We can look to guidance again for a new build and spray intumescent paint on the beams if we choose to. External fire spread, we can classify what cladding we need, and we can decide what we're going to put in the building for fire service, and we can widen roads while we're building it. Big challenge for us, and certainly in what Sean and I look at very frequently, is in existing buildings. We're looking at what is currently in place for these things. We're benchmarking against guidance, but we're looking at reasonably, do we have appropriate means of escape? Would the fire service be able to, again, reasonably use facilities in the event of operational firefighting, and do they have reasonable provision in the site to access and move around? One quick note I want to make, it's actually one of my final notes. I'm looking at the watch. I've gone through pretty quick. I think I started a few minutes early, didn't I? But one point I always make about fire, and I highlight this point as one reason I enjoy working in fire so much, because I love what I do. And one of the reasons for that is the building life cycle, and particularly the fact that fire safety is involved throughout the building life cycle. If we consider the building life cycle is hopefully something that's familiar to most of us. If it isn't, I'll do it super quick. If we take any building or piece of land and we consider it throughout its life, it will go through an element of being designed. It will be constructed, so we'll have a construction phase. It will be occupied, and then it will be demolished or renovated, at which point it goes back to the design stage again. And we talk about the building life cycle an awful lot in industry and in academia and every piece of work that I do. And I always like to highlight the point that fire safety never leaves the building life cycle. During the design, we have a huge element to play. We have a huge part to play in what goes into that building to ensure fire safety. The 5 functional requirements we just discussed are 5 of them. We design the building to comply with relevant codes and standards. We design performance-based solutions in there to ensure that the building is safe insofar as it reasonably can be. During construction, and again, I gave a lecture yesterday about this at the university about construction site fire safety, and one of the teams we have at Delta actually is specifically construction based, going out to construction sites, checking that, first of all, construction sites are themselves inherently risky, so mitigating that through risk assessment, but also the features we have designed in at design stage, making sure that they're being installed or implemented, as we call it, correctly. So if we go to all the effort of writing a fire strategy and we want X, Y, and Z in the building, we have to go during construction and ensure the onward chain of custody of that design. The golden thread, again, I'm going to say, is being constructed. We're heavily involved during construction in fire engineering. Once we go into the occupation of the building, we then continue to manage fire safety. If you walk into any building, you'll pick out exactly what they've got. Fire extinguishers, call points, fire signage, all the materials are cleared, the risk of a fire exit being blocked. All of these things are considered throughout the occupation phase. And then in demolition and renovation, we go back into, if it's a construction site, we have to consider all that again. If we are renovating an existing building, we're back in the building life cycle to construction and back again to ensuring, are we building the things back in that we're intending to? I was looking at something over the weekend, actually. Somebody has opened up a floor, commercial unit, ground floor, resi above, opened up the floor, realised it's got timber inside there that wasn't in the drawings. So during the construction, they've identified a new fire safety risk for us to now consider in our fire strategy. How do we protect that? So a point I like to sort of end on, actually, about the building life cycle and how fire is involved throughout each of those stages. To summarise then, very, very much fire engineering 101, the quickest run through you could possibly do. And I somehow came in under time as well, remarkably. Fire engineering, going back to my first spider diagram, is this multidisciplinary field. It's a multidisciplinary approach, drawing on all the sciences, everything else that we do, understanding of building design, psychology of people in buildings, how do humans behave, all those different disciplines coming together, seeking to reduce the likelihood and the severity of fires. We have to look holistically. If we look at one floor of a building, and again, I had this, let's not call it an argument, but it was an argument about, can you write a fire strategy for one floor of a building? I said, yes, we can. But I also need to understand everything else that's happening. Because if there's a fire on that floor and everybody evacuates, where do they go? What's the consequential impact once they enter the stair and people evacuate? So holistically is really important, or holistic is a very important word for us in fire engineering. And then to finish there, it is both a scientific and an engineering discipline. So we are involved in the design and also the primary sciences that sit behind that underpin all of the design work, as well as increasingly a legal and a regulatory field. 4 years ago, I didn't think I'd be a law lecturer, but I now teach law at a university, and that's because I have to know it for fire engineering. And again, I think that might be my last slide, but going back to the points we had earlier about we have to understand the secondary legislation should we make clients aware. My opinion on that is we have a duty as competent engineers to understand the frameworks that we work within. We do have to understand these days all of the legal requirements we have. And I'm actually really grateful for the fact I teach law, because it forces me to be at the forefront of it and understand those requirements. So I'm weirdly grateful for that role that I've got. So Sean, I trust everyone's now an expert and there were no further questions, but I'll refer back to you and you can throw some at me if on the off chance there were.
Thanks, man. Yeah, that was really good. I had I got a sense of a bigger picture. Like, I don't know about anybody else. I know bits of stuff. So sometimes I know a bit of the structure, I know a bit of linings, but seeing the whole bigger picture and how it comes in made more sense. And then obviously for me raised up loads more questions. Trevor wants to know, just first and foremost, because you seem to be in close proximity to Grenfell and now living near Bradford, he thinks you're a fire risk on its own, so he wants to stay well away from you and needs to know where you are in the country. So stick away from the northwest, Trev, you'll be fine.
Yeah.
And then Peter, I hope I'm pronouncing that right. Do me a favour, raise your hand. I'll see if I can turn your mic on, turn your video on, because Peter was the only other guy who come in with a few questions, and I think it'd be easy just to get you involved there.
Sure.
I've got a few, if that's all right, going through. What do you guys class as a tunnel, or what's the definition of underground for you guys? Because in my head, when you said tunnel, I just thought of like a highway and walking underneath a highway, for instance. That would be a tunnel. But would you guys have the same classification as that as what we would?
Oh, that's an interesting one. Relation to the subsurface regs that I talked about, or just wider generally, what would be a tunnel?
Yeah, wider generally. Like, so is there a limit of you need to be 3 meters underground or a soil beneath, or is it open into the air, or is it completely submerged? Because I know, for instance, we have differences in terminology of basements, if it's completely concealed or not, and how we treat that.
Interesting. We're sort of the inverse of that. So a basement is 3 meters below ground or more than 200 meters squared plan area. We then have basement ventilation requirements. A tunnel itself, tunnel fire safety is one of the most complex areas. It's to do with the length of it versus the width of. But broadly, for the actual design, we consider that a basement. So it's that 3 meters below. The biggest risk for us with tunnels or basements is the lack of ventilation. And tunnels especially have an odd form of ventilation, which is usually forced from one end, encouraging flow. So think about like a tube train, for example. You stand on the tube platform, you get that blast of air. So I'd refer to my basement answer really, which is the 3 meters below, but broadly it's defined on, is it ventilated or not? If there were a fire in there, would it become unventilated? And is there then a risk that sudden influx of ventilation gives you increased fire?
Cool. Makes sense. Linings of the buildings, and this was kind of a bit of a two-parter for me. I was thinking of build-ups in terms of, because for us, build-ups are really important in terms of, like, we have a structural floor, then we have a floating floor on top, ceilings below, and there's usually like a fireboard, top or bottom or something in there. Now, I know like M&E get involved in terms of specifying build-ups in terms of the not acoustics, the thermal conductivity of it all. So they get involved. Architects are on their bit. Our bit's really easy. It's a beam or slab, whatever it's going to be. But is your role in that purely review, or you actually input into that and say, right, we need that beefed up another 15 mil, or add that in, or put this board on there?
I would get involved in the build-up of it, and the reason for it is because where it's layered in there, what someone will do is they'll stick some fireboard in, 2 layers of gypsum, 12.5 mil Joe, it meets 60 minutes or whatever. But I then think about what am I actually trying to achieve, because what I'm trying to achieve in that case is to protect the structure. So I need it to be orientated in the correct direction to protect your bit. So if I've got a floor, for example, as the example you're using, and I'm trying to put 30 or 60 minutes fire resistance, what I'm actually trying to protect is, if we have a fire on the floor below and it begins to attack that structure, is upstairs safe? So my fireboard always needs to be underneath, protecting from the underside. So I personally would input into, and this isn't an invitation for any client in the world to send me 1,000 photos of 1,000 details to sign off. I would input into, is it in the correct orientation and meet the correct specification? Protection of structure is a really important one, because if we're putting in 60-minute structure and we're using an encapsulation method, so we're going to put some fireboard in, you have to think about, are you protecting it from the correct side? And I've seen this done wrong, where you've got structural beam, but they lay it on the upper side of it, which is not protecting at all from where the fire is actually coming from. Similarly, if you've got a column you're trying to protect, you've got to make sure that I suppose the board is flush to the column. If you've got any fire risk inside of there, it's not achieving what we need it to do. So true fire engineering, or true design for me, is continuing it through. And one point that I didn't make, actually, that I wish I had, and I'll just drop in now, is what a fire strategy is. It's a fire strategy for me is not an approvals document. It's not something that ends at REBA stage 4, because a fire strategy has to be a true, accurate representation of the building. So our fire strategies that we write continue into REBA stage 5 and up to REBA 6, and only at that point do we finalise and demobilise from the job, because it's exactly things like that. If I say the floor needs to be 60 minutes, then I walk away and go on to the next job. If it's installed incorrectly and not reviewed and the details incorrect, you turn up to that building in 10 years, you don't realise actually that building has zero fire protection, nothing at all. So I sort of, admittedly, this is a utopian view. This is the perfect gold standard. I would love to be involved in reviewing all those details. I see it as an important implementation of the fire strategy, having designed it to REBA stage 4, and it's important for the ongoing use of the building that we understand that. So yeah, we would get involved, or we'd seek to, definitely.
You spoke about the importance of protecting the structure, and we had a chat internally the other day about fire breaks out ground floor, you have a 2-hour fire, that fire resistance is gone, then it's on the structure. That structure might not be resistance to fire. So in terms of, and it kind of brings me back into fire service and the beat 5 part, in that, okay, at that point, it could be a steel column that's exposed, it heats up, it buckles, it brings down the building. After 2 hours, or whatever the fire resistance is, are we allowed to just collapse the building? Do we have to think about firefighters' access if they're still working on the building, around the building? Are they aware of it? Like, I'm not saying that we design additional periods for firefighters at the minute in terms of making sure they're correct and they have, I mean, we have safe routes going through, but where are you drawing the line, so to speak, on that? Where do we draw? How do we consider that?
Well, very often, in fact, I'm going to come back to that this afternoon. It's the biggest thing I want to talk about, in fact, in my session, which is a bit more of a technical one about how fires work and periods of fire resistance. But to answer it with an example, a portal frame building out in the middle of nowhere, warehouse type thing, we wouldn't assign fire resistance to. But equally, the fire service wouldn't commit firefighters to it. They would stand from under and put a water jet from outside, a ground monitor. And I spoke to a client about this recently. I said, are you comfortable with that? And they said, does it mean I don't have to intumescent spray it? Then yes. And I said, yeah, but you're going to lose the whole building. That's uninsurable. You know, you'll have an issue. In terms of the period of fire resistance, 2 hours doesn't mean 2 hours in a real fire. And that's my talk this afternoon. You know, I wouldn't stand in a building for 1 hour and 50 and then evacuate. So it's very hard to make predictions of. And if you look at 2 building case studies as an absolute, you know, again, we always look at case studies. The World Trade Center collapse versus Grenfell Tower, okay? The World Trade Center collapsed after 20-something minutes, 23 minutes, because the size of the fire was so significant and the structure had been impacted. But it was rated to 4 hours structure. It didn't last 4 hours in the actual fire. The fire itself was more severe than what it had been designed for. So would we over-design? Yes, for a high-risk building. Would we rely upon it? No, I wouldn't rely on it to say, you've got another 45 minutes in there, guys, on you go, keep fighting the fire. And it's a really pertinent question when we have a stay put policy, for example. We've got a 90-minute structure and 30-minute doors. Everyone can stay in the building. Sean, your eyes have lit up when I've said stay put policy. You know, we don't rely upon that as a true measure of actually how long the building will withstand. So, yeah, double answer from me. Yes, we would over specify, but no, we wouldn't rely upon that in our design.
Yeah, because I write that down as well as stay put. Like, how does the fire strategy include with the stay put and where you consider fires in each part of the building? So that fire on the ground floor, does that then relate to your fire strategy and how you view it? Can you get everybody out? Do you have a stay put policy? What happens then? And that was all kind of linked thinking, so to speak.
Yeah, exactly. Normally how our conversations go, isn't it, Sean, where linked thinking occurs and we go off on a tangent, as we did at breakfast the other day. But the 2 primary things we work out for means of escape are, in its simplest form, and this is me dumbing it down, apologies to all the fire engineers on the call that I'm doing it disservice, but how long is the building safe for and how long does it take to evacuate? And we call that the A set and the R set, the available safe escape time and the required safe escape time. We can quantify both those things. So the R set, required time, how long does it take everyone to evacuate? So let's take the example of a high-rise building. The 99th percentile, the last person to escape, how long do they physically travel for? And all of those different components, we can calculate that. And if we do enough fire engineering, we can calculate how long the building's safe for and compare those 2 numbers and give ourselves a margin of safety, hopefully. That is true fire engineering. And if we get to the point where we've got a discrepancy, if the building is unsafe by the point people are still evacuating, that's where we start to design in new things. That's where we might use a stay put and say, look, we're designing the part of the building to evacuate at any one time, because it's just the building can't sustain a longer evacuation period because people who are evacuating are not in safe conditions. So that comparison between safe conditions in the building versus how long it takes people to get out is that assessment we do an awful lot in true building design, certainly for existing buildings.
This brings me on to likelihood and iterations. So if you're doing a stay put strategy, and how many iterations of, right, a fire might start here, might start here, might start here. How many iterations do you do in terms of when you do that?
That's a really good question, okay? Because what we are taught, or what we are told, is pick the worst case. And I always, my favorite sentence is define X. As soon as somebody says something to me, and this is part of the legal work that I do, I always get them to define it, because I say define the worst case. Because you could have a really significant fire in terms of fire size and temperatures that gives out no smoke whatsoever. You could have an explosion, for example, okay? Very little smoke, but huge amount of flame and temperature. Or you could have a smouldering fire that gives out very little heat and temperature, but a huge amount of smoke. So it's very difficult to define what that worst case is. So I'm not going to give the answer. I do 4 iterations every time. I do 5. It's always 3, Sean. There's no answer. It is simply looking for the worst case scenario. And the way I define it is the consequence of that fire. Because a very small fire in a stair might be far more severe than a massive fire in a plant room where nobody is and it's ancillary to and we ventilated it and all that kind of stuff. So it is very much building specific, but it is about iterations. When I do a lot of CFD modeling of the fires and the smoke control and all that stuff. Most of us probably familiar with CFD. If you ever get a CFD model and it's got one version in there, it says that's the worst case.
What's CFD?
CFD, computational fluid dynamics. So the way I define computational fluid dynamics is I break down the words, right? So fluid is anything that's not a solid at its simplest shape. So fire or smoke is a fluid. Dynamics is how it moves. So how does fire move? Computational, solve it with a computer. So it's a computer model to estimate how a fire would spread in a building. And it's how we design smoke control systems. We put a fire in a building, we construct it, run the fire, see where the smoke is, and that's where we put the vents to ventilate the fire out, ventilate the smoke. And I do a huge amount of CFD modeling. And when I do it, I do 4, 5, 6 iterations, put a fire in the stair, put a fire in a flat, fire in the basement, fire outside that might break in. So there's no golden number I can give you, but it is definitely numerous. Is the best answer. Yeah.
All right. I've got one more question, then I'm going to turn on Peter's mic and camera because he's got like 3 questions and it'll be easy just to add him in. Sure. You put a graph up earlier about the descendancy, the trend of fires going through. So does that feed into your likelihood of how frequent, or the chances of a likelihood of a fire starting? So does that get adjusted each year if you're seeing the trend reduce?
Not from that graph, but I would use data similar to that. So if I was interested in, because there's lots of things in fire statistics, he takes his glasses off like everyone's going to agree, but fire statistics are interesting, okay? There are loads of things hidden in there that are both correct and incorrect. So for example, we have a big element of what we call survivorship bias. So we're interested in the fires that aren't reported, okay? So the government statistics say there were 44,000 fires last year in the UK, but there weren't. It means the fire service attended 44,000 fires last year. Unreported fires are far more severe and far more significant often. So we don't rely upon it as an absolute, but it does give us trends over time. And it does give us useful data. For example, in which part of a flat does the fire most often occur? 60% of the time it starts in the kitchen. That's useful for me in design. Okay, I need to do more work in the kitchen. Balcony fire, what's the likelihood it'll spread to the floor above? I'll use that data. So I wouldn't use that graph as such. I use that for an overall trend. And I use it particularly to look at how effective we are with our solutions. So, for example, how effective were the furniture and furnishings regulations in 1980? Very is the answer. We see a downward trend. Other things in there, like that was when we start doing home fire safety visits and smoking. If you compare rates of people that smoke versus fires, there's a positive correlation as well. So lots you can do. But yes, if we're looking at risk in buildings, we do look at data to see how significant they are and how likely they are to occur, but it's always with a bit of a pinch of salt because it's not a full data set for us with fires, unfortunately, because we only get reported fires.
Cool. Peter, I'll give you mic and camera. So you jump on with your stuff. I'm going to just review the chat because I know there's a few more questions popping up in there now.
Hi, Peter. Confidently said hi, Peter, then, like we're on a radio phone-in show or something like that. Hi, Peter. Thanks for calling.
I did give it him. Hang on. Let me check. I'm sure he's there, unless he's just nipped
Oh,
off.
he's got no mic, he says in the chat. I don't think he's got a mic connected.
Okay, cool. Right. I did write down his questions anyway. So,
all right, guys. Hi there. How you doing? You all right?
Oh, we got you. Hi, Peter.
I got to button up a little bit. You know, just had to dress up quickly. Sorry, guys. How you doing? Very nice. Very informative. I like that. I like all of the data and stuff that you put in all together. That's swell. Yeah. Very good. Yeah. Well, I am a chartered structural engineer, and I deal with design of the buildings. And actually, from the architectural perspective as well, taking it through all of the parts of the schedule of building regulations, right, including the fire ones. But we would like to be, as an office, involved in a little bit more than just domestic little dwellings, right? Going maybe into the higher risk buildings. And I wonder, as you just said now, there seems to be so many different specialisms, you know, like a passive fire protection, or, you know, being a fire engineer. It seems like it's being driven by the legislation, all of the creation of all of those specialisms and businesses behind them, basically. And I wonder, the person like me, being a chartered engineer involved in, you know, in design of the buildings on an everyday basis, how do person like me go into the fire engineering, and where would be the best place to get chartered and sort of in a broad brush cover all of those aspects, like, you know, passive protection and, you know, doing assessments and all of the rest?
Sure. No, that's really a really good question, actually. The chartership, registering with the Engineering Council, is inherently an engineering field, which brings in all the competency requirements, so puts you into engineering design. Lots of those other ancillary areas, for me, this is opinion here, I suppose, not fact, but this is my take on it, are not necessarily the kind of overall. If you review a construction detail, you don't need to know the strategy. You're not necessarily briefed on why that's fire rated. You're told this needs to achieve 60 minutes, does it or not, design the detail. So for a chartered engineer, for me, that is the overall holistic view that you would get from designing buildings and seeing it through the construction phase and all of those things. So that's where I would position myself, going for a chartered requirement. But one thing that one thing I find is important is that somebody who's involved in fire should have some understanding and appreciation of every different field. And I do sessions like this for other areas of the fire industry, because I want fire stoppers, people that physically install fire stopping, to understand why I'm asking them to do it. But equally, I want my fire engineers to know what it's like to fit a bit of fire bat. I want them to go out and physically install it and do it themselves.
Absolutely. And I guess my question is, turning me as a chartered structural engineer into chartered fire engineer. Basically, we want to expand on our business and become chartered fire engineers, as well as you know, as chartered structural engineers. And what would be the easiest, the best way forward to go? Maybe which institution in the fire engineering realm or university to contact for the guidance?
So Institution of Fire Engineers, I think, is where we'd go to here. Go to the IFE and look through and benchmark the UK spec for fire and structures. Now, it's interesting for me, having reviewed the structure spec, that there's quite a lot of fire content required in there. So I benchmark those two against each other, go to the IFE and see what the requirements are there. Opinion here again, anyone can jump on me if you choose to, but I'm going to caveat by saying it's my opinion. Over the last few years, there have been lots of people come into fire from ancillary disciplines. I see this, for example, on the master's degree that I teach. 3 years ago, it was all fire engineers wanting to get their chartership. Nowadays, it's building control, architects, structures, mechanical, going into fire. For me, it's a really positive thing, because I think that fire needs to learn from those disciplines. We need more architects to come in and tell us about architecture. We need more things like Sean and I are doing. We need you, Peter, to come in and tell us about structures. So I actively encourage it. I think more people should come into fire and understand it, and remove this kind of blanket we have where people don't share between disciplines. So to answer the question direct, Peter, it would be the IFE, their requirements that they have, and encourage you to look into building design for fire, as well as, I think you probably align with me on this, the minutiae in there as well. So how do you physically install a fire door, as well as how do you go out and And
yeah,
and
the
specify what it
whole
is.
thing is very important. You know, taking it from the general perspective of the strategy to the actual solution and implementation on site. That's absolutely that. We charted with SPHStructures, and we have a specialism in fire part that we could sort of go through, but there's not much information. It's not really propagated or promoted by the institution anyhow. You know, so that's why I thought I'll ask the experts about that. And that's what you just said. It leads me to the other part when we often deal with specifications for let's say escape routes in part B.
Mhm.
And there is this, and it's always been a dissonance and legal battle between the specifier fire engineer and the building control on the other side, who very often lean on the approved documents. But obviously, there's always the gate that you can go through as a specialist to to specify a different solution. And
Yeah.
up till now, till the Building Safety Act went in, the only way to get out from this impasse, if you like, were to go to court and go against the health and safety executive, right?
Mhm.
Is it now the case that there's actually more onus on or more power given to the specialists that they can actually with their work with the design and specification that they can overrule the building regulation without going into legal battle?
Oh, I'm going to use my phrase again. I'm going to say define power, because I don't know
Yeah,
of actual power that I can do it. What I can say anecdotally is I'm being given that responsibility an awful lot more. I.e., it says fire, so Joe, your name's going on it. Are you happy? We've already filled in the form, sort of thing. I think there is more onus going on to the designers. I don't know about power. I don't know that I've been granted any more right to do that, but certainly more of an expectation and a responsibility for doing it. And I know contemporaries in other industries, including structures, but all other design disciplines, we're finding the same. It's being kicked down to us as designers to say we've got more responsibility. So yes, I'm definitely seeing it. I think. Am I comfortable with it? I am personally, because I know that my name's going on the right thing. Am I comfortable with that in an industry shift? Perhaps not, because I think lots of people are being asked of, and there's this. It says fire, so ask the fire engineer. So positive and negative shift, but yeah, I'm definitely seeing it. I think, Peter. Yeah. Do you get it in structures? I'm going to ask you both actually.
Yeah.
Is that something you see in structures as well?
Not as much of it. No. It's always a battle, and my question actually comes out like in the structures. If you want to use an innovative solution, that's something that no one really thought about before on connection of different materials, and like glass, for example, using glass for structures. There's not much of the codes and anything that could actually protect you or give you the backing in the code that you could show to the regulator, and then you go with straight no, you're not gonna do this. And then where you go from there. You can put your name down to it. You have all of the calculation. You have the experience with the material. You have testing or whatnot, but they still say no.
Yeah.
And there's the only way to push that design forward, or maybe solution in a fire protection scenario. There's no way really to go from there except to go to court and fight between health and safety executive and you and your solution.
Yeah, I'm seeing a lot more. So yeah, I'm definitely seeing, not to the level of courts. I've not seen that as such, but definitely there's an engineering judgment needed. You're kind of in a position to be able to do it. Will you do it? And that is an area, interestingly, going back to a question from earlier this morning, where I've seen peer reviews being asked. So if you do something that's innovative, which is something that's happening in fire a lot at the moment, particularly in existing buildings, take it down the lab. We're fortunate enough to have our own research lab, so we do some of this testing ourselves at Delta, right? We'll go and test something and give actual physical data for what it looks like. We're then asked, can you get a peer review of this? But in actual fact, I would also ask for that as well. Would somebody else check my homework for me, if you like? So yeah, a shift towards that. And there's another trend in fire I've not mentioned that I'll do in 25 seconds. That fire often hasn't kept pace with the rest of the world. So fire has been understood for tens of thousands of years, as we know, but not.
Oh, he's freezing.
Maybe I take my camera off. There's too much information going back and forth. We extend, we went past the clock anyway, so maybe that will help.
Oh, have we lost you, Joe?
No. How's that? Am I back?
Okay, you got audio back? Yeah, okay, that looks better.
Yeah, is that all right? Sorry, Peter froze a bit, and I think I did as well. I don't know where I got to. The answer was yes. I find that in terms of being asked to do engineering judgments and things. Yeah.
Oh, right. We're going to pause there. Quick break. We did have 15 minutes in, so it's 11:05 now. If we convene back at 11:20, and I'll hit the ground running with the intro to structural engineering as well. All good?
Brilliant. Cheers, mate. See you
Cheers,
shortly.
John.
Thanks, everyone.
Right. I'm going to run with the intro to structural engineering now. And this was a bit weird for me because I haven't taught at this level for a while. Right. Get rid of you there, Joe. Okay, high level overview of structural engineering. So as with, come on, move. There you go. As with Joe's, if there is anything you want to know about structural engineering, or you've had a question, now's the time to ask. So it might be, I don't know, what is over engineering, what is under engineering, what is ULS, what does SLS stand for, what is CLT, what is a moment connection, what is a pin connection, anything like that, drop it in the chat. I'll feel free, I'll pick up what I can after in the Q&A as well. No stupid questions here. Half the time you ask a question, it might just make some things click together for you. So more the merrier, honestly. I'm going through the building regs route as well. I figured that if I'm talking to fire engineers, clients, everybody else, people know the building regs. So I'm going to try and make this as practical as I can. I'm not going to go theoretical because it will just bore you. So I'm going to try and make this as practical and show you from practical application how we interpret the building regs and what we do to discharge each point. So everybody's seen the building regs, 2010 building regs. This is what we all work to. We're part A, and within part A, I'm just going to flick to the next slide. Schedule 1, part A, there is about a third of a page that covers structure. You got A1 loading, A2 ground movement, A3 disproportionate collapse. That's it. I'm calling that new building requirements, because if you follow those requirements for a new building, you're not really going to go wrong. When you read through the rest of the building regulations, you have clauses 3, 4, 5, and 6 that relate to building work and material change of use. I'm going to call those refurbishment works or refurb works. And they basically push you back. They're for existing buildings, but they basically push you back to Schedule 1 and say, look, comply with this where you can, depending on the form, structure, and consequences of the building. So that's kind of what we work through, and I'm going to work my way through those. So A1 loading, building shall be constructed so that the combined dead, imposed, and wind loads are sustained and transmitted by it to the ground. What A, safely, and B, without causing such deflection or deformation of any part of the building or such movement of the ground as will impair the stability of any part of another building. So I don't know if you guys are the same as me, but sometimes you've got to reread this stuff twice just to get it through. Basically, part A, part A, to do it safely, we call that ultimate limit states. So we have, that's our set level of safety, whether it's bending, whether it's compression, whether it's intention, however it's working, this is the ultimate limit state. It's got to work. That is, we're not allowed past that breaking point, so to speak. So we call that ultimate limit state. And then the bit about deflection, deformation, we call these serviceability limit states, SLS for short. Now, if you're at home or you're at work right now in your homes, you're sat on floors, walls, roofs around you. Your floors can only deflect or sag a certain amount before the plasterboard beneath them starts cracking, or before they become bouncy, before walk across. And as humans, we're very susceptible to vibrations in floors, for instance. So vibration and deflection, there's serviceability. Most of the time in new building, I would say it's your SLS limit states, how stiff something is, how much it moves. This is what we design to these days. So this is what dictates new build design, not the ultimate limit. That you could build a building safely, but it might move, it might crack, it will still be safe. Serviceability is what we design new to, and there's an important differentiation there to understand between the two, because that's what we work to most of the time. So ultimate limit states are with a factor of safety on, and then serviceability limit states are basically everything that's scrapped off. This is as it's working in its natural state, so to speak. And that's how we apply the two conditions. Now, I like a visual representation. So In terms of dead load is the self-weight of the structure. So it's the self-weight of the wall, self-weight of the floor, self-weight of the foundations, the roof, the beams, everything that goes into it. We call that a dead load. That includes floor finishes, wall build-ups, roof build-ups, and the like. Imposed loads are wind loads. Anything acting externally on the structure that is variable, basically. So a snow load is a imposed load. A wind load is an imposed load. People walking around building is an imposed load, and we have set values on that we take from codes and everything else. Now, basically, as structural engineers, we're just applying Newton's third law, which is every reaction has an equal and opposite reaction. If it doesn't, the building moves, it falls down. This is how collapses happen. So we are very much Newton's third law kind of guys. And so when we look at a building, we're basically transmitting all the load. So if the roof was spanning from here to here, it goes into the walls, go into the wall, into the wall, into the wall, down to foundations, which aren't shown. That's nice straight, that's nice and easy. We like nice straight and easy, keeps it simple. Where we have a break in the load path, that's where we need to add a beam or a transfer structure or a podium, it's sometimes called, depending on the form of construction. And it's these little tweaks that we have to pick up, move the load around. We basically chase the load all the way down the structure. And in a nutshell, that's what we do. But we do loads of calculations to make sure everything bends, moves, compresses, stretches as much as it needs to. Now, when we look at wind, we live on an island. So we work to Eurocodes, and how we interpret wind is different to how the guys on the continent interpret wind. So for instance, like a landlocked country would exhibit wind acting on their country different to how we would. Now, there's different wind velocities around the UK. Basically, if the further north you go, the windier it gets. And we typically design for the worst case wind force in the last 50 years. So you are looking, and that's when you look over the data of the last 50 years, it hasn't really changed as much. We looked at that recently in terms of, is that a question we should be asking ourselves as part of a risk as well? And we always look at the orientation of the building. So wind can obviously act from any direction in the UK. So north would be 0 degrees, east is 90 degrees south, 180, west 270. Now, if you're about 240, which is basically coming up from between Cornwall and Ireland, if you're coming up that channel, that's the worst case wind load coming into the UK. So I know that if, depending on how my building is orientated on plan, as you look down on it, it might be picking up a full load of wind on one face, or it might be slightly skewed. Okay, can I take a slightly reduced wind load here? And this is how we call that lateral wind force. This is how we consider the overall stability of buildings. And when we talk about lateral wind loading or lateral force, this is what we mean, and it leads into overall stability of the building, how safe a building is from overturning a wind load or sliding and the like. Snow loading, very similar. Further north you go, the worse it's going to get. And we have snow maps across the UK that we work to. And basically, again, we're following similar. We're working to the worst case snow load from the last 50 years. We keep an eye on fluctuating changes in that. Obviously, different loadings around the UK. And then snow load greatly differs depending on the shape of the roof structure. So if you have a flat roof, it is obviously going to attract more snow load than a pitched roof, depending on the pitch of the roof. Parapets around walls, snowdrift. Snowdrift from one roof down to a lower roof, snowdrift from a pitched roof onto a flat roof. We call that accidental loadings. So in the worst case, a very accidental loading, you might get a very high concentrated bit of snow in one area. That might cause your roof to overload locally, or could damage, and it could give you local considerations to think about in your design. I was lucky enough that when I first started my career, I was in a timber truss, timber frame designer, manufacturer, and erector. So I got to see the whole process when I first came out of uni. And there was a truss department within my team, and I loved it. These guys were doing 3D models of roofs, drawing all the trusses in, and it was a proper 3D orientation, trying to get a triangular grid on a 3D scheme with all the bracing and everything goes round. And then they'd come to me and go, okay, give us the snowdrift calcs. And I was there like, I don't know what you mean. And that triggered my learning process into all this. But I learned loads from the truss guys in terms of how they frame roofs, how they approach it, the different forces involved and everything like. And it's a real art if you can do it well. So dead loads. Now I've thrown up this blank drawing because I want to talk about scheme designs. Now, when we talk about scheme, you will get a blank set of drawings like this, and in my head, I'm wondering how to frame this. So this dictates my dead loads, my build-ups. How am I going to make this? Is it going to be steel? Is it going to be concrete, masonry, timber? What's the best form of construction? Now, I'm going to skip about 18 years of experience and tell you it comes with the numbers. Okay, my first boss used to call this get a feel for it. You'll get a feel for the numbers. You will know that a timber joist floor can span 4.5 meters as a stair trimmer. When you go up to 5 meters, it's glulam. When you go to 5.5 meters, that's a steel. I know that because I did those designs 20 times a day for the better part of 4 years. That was getting a feel for numbers. When you start working with different materials and you start running the numbers, you start to see what dictates design. So for here, this was actually a 2-story existing concrete frame that we were extending by a further story, and this was the layout for the additional story. So architect had drawn nice walls, everything kind of spans roughly, all the bays are kind of similar width, so it adds to a lot of repetition, which is good for us. We can keep all our joists the same length. We can make these all load bearing if we have to. Corridors nice and uniform, great, all that works. This area is a bit open, and that span there is a bit greater than that span. So I know I might have to add additional beams through there. Is that a problem? Okay, not really. Somewhere local. I can probably come off that column onto that wall. Yeah, that works, great. And then same down here. I'm missing a wall through here. So I know I'm gonna have to put a beam through there. Okay, I'm missing that column there. Okay, I'm gonna have to consider that. But really, that's when I'm looking at it, they're the only real considerations. I could make that a load bearing element, load bearing walls quite easy, and I could form that in masonry, timber frame, or lightweight steel studs. They're your traditional load bearing wall elements. As this was extending an existing building, I don't really want to go for masonry because it's very heavy. So I'm looking at a lightweight solution such as timber frame or lightweight steel studs. And I could probably do that, and I could probably frame it out. Now, the architect in this case, they'd actually drawn in the columns around the perimeter of below, and we've got 2 rows of internal columns that run from there to there and run from here to here as well. Now, I would say if this was a bigger structure and I needed to maintain the column grid below, I'd be looking at that as well. So I'd be like, okay, it looks like he's drawn all the walls on the column lines. So I'm like, okay, great. So can I put a column in there? Yeah, I could probably hide one in there if I had to. I could probably hide one in here if I had to. In here, great. And then on this line, okay, I might struggle a bit there. That might be a nice chat with the architect to see if we can shift something about. There's okay, there's okay, there's okay. We'll do that. So this layout lends itself to both a load bearing wall structure and a frame structure as well. So I could easily make that a steel frame coming off the existing, or I could extend the concrete if it had enough strength in it and make that. And then all these walls then become partitions. And then I put in, I don't know, a 200 or a 300 concrete slab, or I put in steel beams, a frame between each of my columns, and then I put floor in between all the beams. Making this decision early is going to dictate everything you do going forward. So going through the Reba design process or the iStructures design process, all the work stages, stage 1, 2, 3, 4. At stage 2, you're probably going to do this exercise that I've just done at a high level. So you're going to see how the building's framed, what layout it suits, what construction it suits. And there are some layouts, there are some buildings that are better suited as concrete frame, better suited as steel frame, better suited in timber, better suited masonry. And it's just knowing, and obviously you get hybrids of each, adding in steel portal frames or steel grillage or transfer structures or whatever, you get a bit of hybrids in between, but it's knowing the best scenario for which. And when we look at, when we talk about scheme design, it's this. So this, doing that exercise will get firmed up in stage 3. So I will turn around, if I wanted to go to frame structure now, I'd tell the architect, you know what, steel is quite cheap right now. We should push a steel frame right now. I need that column there. Can we make that tweak? Otherwise it works well. We get that set, and that's all your main elements, your main members set, they don't move. And then that should feed you into stage 4, technical design, and you start detailing it all up. But once that's set, then you do your build-ups. Now, back in the 60s, the British Standards Institute very kindly went round and weighed everything. And so you have a whole standard full of weight of plasterboard, weight of copper pipes, weight of slate tiles, weight of clay tiles, and everything in between. And these 3 images are taken from the Robust Handbook, which a lot of architects use, and these are replicated as normally as 2D build-ups and drawings. And we're basically going through and we're just putting the weight of everything. We count everything up, we put the weight to it, and even on the roof, we're working out the weight of tiles, battens, and the rafters below. And we do this in order to do a load takedown through the building. When it comes to the imposed load, we dip back into the Eurocode and we say, right, Eurocode 1, actions and structures. This talks about density, self-weight, and imposed loads for buildings. There is some measurements. There are some values you can take for the self-weight of materials in this code as well, but that one's much more comprehensive. Never really use that for the self-weight so much. And then the imposed load, there's categories depending on the use of your building. So residential would be classed as A, fairly low. These are the loads that we take and they recommend to take. So they're saying, right, for floors, you should be taking 1.5 to 2. They've underlined and bolded some values saying this is what we recommend, but when you go to the national annex, so obviously we might have different considerations to France, Italy, or Germany. And I can tell you now, the UK annex says actually use 1.5. Historically, we've always used that here. You're good to use that. Great, no problem. That's an area load, so we apply that load all over the floor. And then this is a point load, which we apply to the worst case point on the floor, just to make sure that it has local resistance on the floor. And then, so A is all residential, fairly low loads. And then as you increase in the usage, high risk of the buildings, the loads increase that you have to work to. So B are all offices, and there's a difference between the load you take on the ground floor and the office space above that. C are areas where people may congregate. So this is stairs, corridors, anything like that. We include allowances for wheelchairs, electric buggies, all those loadings as well. D would be shopping. E is storage. F and G are lightweight and heavyweight vehicles, and then H takes you up to the roof. And then there's nothing in there about plant loading, so you have to make another allowance on that. You speak to the M&E guys, see what the plant is, and you go through that. So this is us building up our loading. So for instance, in the instance of a beam and block floor with a screed on top, we'll probably take if we know a load allowance, would go to the codes, take the weight of the screed, take the weight of the DPM, take the weight of the beam and block flooring and the ceiling, which is taken, the build-ups are taken from part E, same, I think it is in the approved documents. And then we'll apply a 1.5 load here. We call this characteristic load. Characteristic loads are denoted by K. It means there's no factor of safety applied to them. This is the load as it is. You build it, you stick up the scale, you should be getting somewhere close to these figures. Then you've got your design load, which is everything denoted with a D. This is really important in our calculations because we add the factor of safety on. So this would essentially be our ULS, ultimate limit states, and this would be our SLS, serviceability limit states. We use these loads for that, and we use these loads for design. Now, your K and D, so if I'm picking up another set of calculations from an engineer, this is the first thing I'm looking at. I'm checking what loads you do, because it's really easy to be conservative on this. Now, when you can be a little bit out either way. It's better to be out if you're slightly over. So if you allow a slightly heavier load, then you are slightly over engineering it, okay? And then over engineering means I think the structure's heavier than what it actually is, but I've designed for that. It's not going to move, all going to work fine, no problem. Obviously, you want to get this as accurate as you can. We strip it right down, we get it very accurately. So if you over engineer it, that will be a 6 or a 7. You don't really want to go up that far. People might take a 6 rather than 5.82, for instance. But then if you under engineer it, if you get any one of these wrong, and I've seen that equally on some build-ups, then you're coming at 5.5, 5, 4.5 maybe. And there's silly mistakes, but silly mistakes here can impact you every step of the way throughout the rest of our calculations. So this is the first thing you need to get right. And if you under engineer, then you're basically thinking unwittingly, your building's heavier than you think it is. So things are going to move more than you think they are. Things are going to work harder than you think they do. And that's what you don't want. It's fine being on the over engineering side. No harm done. It might cost a little bit more here and there. Usually doesn't, but you definitely don't want to be the underside of it. So this is really critical from that point of view. Once we've got our loadings, we worked out the load for the roof, the floors, we'll go back to our layout, and then we'll just mark up a loading plan. So we say, right, our dead load across this whole floor is the same. We're going to use the same floor all the way through, but our imposed load is going to change. So all the yellow is going to be residential loading, and then all the orange in between, that's our corridor loading. So we're going to go a little bit heavier on the corridor for imposed loading, but over here we're going to go 1.5 and here go 3. Now, I've denoted here differences. These are terms you might hear in meetings. Like I've thrown them out a few times when I talk about area load, line load, and point loads. And it's for us, that's how we differentiate between how certain elements work and how the load is redistributed around the structure. So your area load is the load per meter square. So you times that value by a unit length, and you get a line load. That line load is a length acting on a beam or a wall, and then the point load is the reactions from that. So that's best summed in this diagram. So when we talk, so if I'm doing a load takedown and I'm working out how much load in the building and where it all goes, I'm looking at my area load. And I'm saying, right, I'm going to span my floor from this wall to that wall. I'm going to assume half the load goes into this wall, half the load goes into that wall. Right, that distance times the area load gives me a line load. That line load I can apply at the top of the wall, and I can now design my wall. Or if I'm over here, I can take half that floor load, maybe a little bit of this floor load because it's spanning that way, and then I can take that beam. I know the line load on that beam now, and now I can design that beam. The reactions of that beam sitting on this wall and this wall are what we call point loads. So concentrated loads that we have to chase down the structure. Now, that basically brings us back to this diagram. We got our area loads, we're converting them into line loads to do our floors, and then where we hit somewhere like a transfer in here, then we're talking like a beam or something similar. So I might have a beam spanning from here to here, for instance, and that might give me a point load reaction there and a point load reaction there. And it's really important. And that's, in a nutshell, that's what we do. We chase all the load down, we make sure everything works safe. And then we also talk about lateral stability from the wind in terms of safety. So that predominantly sorts out the vertical. We also need to sort out the lateral to make sure it doesn't move anywhere for that as well. Now, when we talk about the wind, there's a few ways. I've ripped these from an iStruct publication, but I still think they're great diagrams to demonstrate how the load works and how buildings work as a whole. So at the top, we have, this is how wind can affect a building. Any building height, they all act the same principally. It just depends on what material you use to resist the wind. Now you have overturning, you have racking, you have sliding, and you have twisting or torsion. Depending on the layout, depends on how much you're going to see from each one of these. Now, your heavy structures like masonry and concrete aren't necessarily going to overturn too much because they're pretty heavy. You've got more weight in there. Overturning is going to affect lighter weight structures such as timber frame, maybe tall, slim timber frame houses. You see the Taylor Wimpey's and the Barretts build big housing developments out of these things. They're always very tall, very narrow, 3-4 stories. They always take out all the cross walls, and they all struggle for stability in terms of overturning that way. They also rack. So if you build walls on top of walls, that's called racking. They just want to start sliding. They all kind of move like that, which is the top right corner. Sliding, the whole building just shifts. So we have to look at the interfaces between all the floors and the walls to make sure we have enough, because your wind will accumulate down. So wind hits here, goes on the structure. Wind hits here, goes on the structure. By the time you get down to the ground floor, the interface between the ground floor and the foundations, all this wind load is going to be resisted by that connection down there. So that's sliding. And then depending on the layout, twisting and torsion, best demonstrated in, say, big concrete cores. So you'll see concrete cores and you'll see smaller columns dotted throughout the building. Depending on where that core is, if it's central within the building, you know, all the wind load acts along the centre line of that. As soon as you shift that core out, then you're adding torsion into the building, and that can add all, let's call them hidden forces, all additional forces generated by how hard the building's working to try and stop twisting, to try and stop that torsion. So when we jump into the bigger diagram, wind hitting this face is going to hit these columns and it's going to put these columns into bending. Those columns is going to throw half the load up onto the roof. This column's going to throw half the load back onto the floor. And in this case, we've got a truss basically on the roof. So it's hitting these columns and it's trying to redistribute through. So the wind's pulling it from there, pushing it through there, and we get over to here, and this is like a vertical braced bay, vertical truss, brace bay, what they normally call it. And you're looking to get all the load, and on the floor diagram, these acting as deep beams from here to the other end. There'll be another one of these at the other side of the building. And we're looking to transfer the wind load through the floor deck, through the roof, into these brace bays. And so the wind will kind of hit through here, travel down, travel down, travel down, back into the foundations, and then you're looking for the foundations to resist the sliding effect and everything through. That's it. Nice, simple, nice, easy. Frame buildings, low bearing wall construction, whatever it is, principles are all the same. Chase the force through. Nice logical procedure to it, and you can't go wrong. I'm throwing this in as you may see some of these other engineers demonstrate these on their social media or websites and wherever else, and it is computer modeling. Now, that whole exercise, we have computers to do. So, for instance, it's more applicable in, say, concrete structures, which, because concrete structures have reinforcement running in two ways, the load distributes less linear, shall we say. It's not a straight line, it all goes here, all goes there. It's more of a load spread to it. So we use computer modeling for that. And there's a big issue in our industry at the minute about over-reliance on software. And basically, you can build a model, you can build a building, you can apply all the loads, hit a button, and it will churn out, okay, in this instance, this is deflection. So I know I'm getting loads of deflection up top, but not so much deflection down here. And then this instance, this is brace bays working in X direction. So wind hitting basically the smaller elevation of the building. These are what's working, and this is how, and then it will tell us how hard it's all working in event. Really powerful, really great tools if you can use them correctly. If you can't do the hand calcs to double check what this is kicking you out, they're useless. There's no point. Its computer says yes, off you go and build it. The big case in Hackney Wick, I think it was Taylor Wimpey's 60 million development that got demolished. I think nobody's come out and said what it was. I think it was because of this. When I went on site to have a look at it, when it hit the news, I could see from the hoardings, it looked like two engineers had, one engineer had built the bottom, another engineer had built the other on top. And I know, because that was a concrete building, I know the stress would have redistributed within the model, found a way around, found a way working, computer says yes, and they're going, okay, great, off we go, build it. It's really dangerous. They're really powerful, but they're also really dangerous at the same time. So I think we're heading for a bit of a problem in the industry with that, but that's where it comes from. Leads us into A2 ground movement. The building shall be constructed so that ground movement caused by A, swelling, shrinkage, or freezing of the subsoil, or B, landslip or subsidence, other than subsidence arising from shrinkage, insofar as the risk can be reasonably foreseen, will not impair the stability or any part of the building. Right, I'm going to break these down into two bits. Now, I'm going to deal with swelling and shrinkage to start with. Geotech guys might not like me for this, but basically there's two types of ground. You've got your clays, and then you've got your sands and gravels, and then you've got everything in between when they all mix it up. Your clays, which is what half of London's built on, is that will shrink. That will shrink and swell depending on the moisture content within the clay. So when we talk about shrinkage and swelling, we have that consideration. Now, where there's no trees about, during summer and winter, there might be, I don't know, a 3 or 4% moisture content change within the soil. And you are going to see that change mostly anywhere between 450 down to a metre-ish kind of like range. That's why whenever you see foundations that come in and we're in the clay environment, we always take them down to about a metre for this reason. We don't want that movement during the summer and winter months, because in 1970 there was a big heat wave through the southeast, and all the buildings in the southeast, all the homeowners, everything just started cracking. All the insurance companies then went, whoa, we can't keep paying out this. Where's all this come from? What's the definition behind it? What's a crack? Where does this come from? What's structural, what's not? And then the BRE basically did a big research paper on it, and they come out with crack classifications. What's aesthetic? What's serviceability? What's structural cracks? And then they come out with the recommendations saying, right, you're all in clay. Clay shrinks, it moves, it swells. Take them down to here. And then clay itself will have different shrinkage and swelling properties called plasticity. So high plasticity, take it down to a meter. You can go 0.9 meters for medium. You can go 0.75 meters for low. The extra 250 mil of concrete, it's not going to make a big deal to your building. So most engineers will take it down to a meter. You know you're good then. You don't have to be on site checking it, the contractor to pinch an inch here and there. Trees, however, can cause shrinkage and swelling as well, because they extract moisture from the ground. Now, depending on the species of the tree and the maturity of the tree, some trees are more thirsty than others. And depending on how close you are to the foundations, they're going to be a pain. For new buildings, not necessarily a problem, because you normally have an arboricultural survey or arboriculturist involved. And even if you did want to do any landscape and tree planting, those guys normally go, right, here's the tree root protection zone. We can't put any buildings here. And you stick the trees out as far away from the building as you can. And it's not really a concern. Existing buildings, this is a big problem. And it's normally, I'm going to use the London example again of like a nice featured road with trees and the pavement, and then all the trees have popped up all the paving slabs, and they're basically rooting underneath the buildings now, and they're causing crackings to the front or rear facades. Gardens are a good example as well. So, but the trees, well, you're probably up to 7-8% maybe moisture content, but this is over a much greater depth. So even if you're in clay as well, you've got the clay plus the trees trying to obstruct moisture, and then the shrinking the movement between the shrinkage and swelling between the seasons is too great. They need to take you down to about 2.5 meters here to mitigate the risk of any movement from the foundations. So that's a lot of concrete going in the ground. And when you're going into, say, more than, I think it's 1.5, 2 meters ish, you're into temporary works in terms of you can't dig a hole that deep and expect the soil not to fall in on itself. So contractors need to be especially careful. You need to be careful on how much soil concrete you put in the ground. And this may be the tipping point where you go, right, I'm going to put piles in rather than mass concrete, and you look at alternatives to foundation design. But that's shrinkage and swelling, and there's some of the considerations that we have to do. Freezing of the subsoil. Short answer, anything within 450 mil from the surface level, you're going to be, you're in the heave, it's susceptible to frost heave. So frost heave, your top 450, mainly top 400, let's call it, if your soil is going to freeze during winter. Once that starts thawing out, anything you've got bearing in that zone is going to move. It's going to crack. It's going to move everything above it. This is more applicable, say, for garden walls, or anything kind of like there that's maybe garages or out sheds or outhouses, anything like that, that aren't heavy, don't need a lot of load. People dig a small hole, stick it in, and off you go. It's also applicable to Victorian townhouses in Bath, in London, and half London are built on what we call core-board foundations. So these are core-board foundations. It's bricks that step out 1 or 2 courses, and I don't think it's a coincidence that these things are always around about 450, 600 mil below ground level. Now, bearing in mind Victorian era took you up to 1900 before the Edwardian era kicked in. And the Edwardians, they basically straightened everything up and made it work better. But the Victorians, they basically, I think they took masonry to its limit. They figured out that you could build a 3-story masonry house on these teeny tiny foundations right at the bottom, and it wouldn't move. They knew if they had to go to 4 stories, they needed to dig down, and they needed to offset that load into the ground, and then it wouldn't move. And that's how they get a 4-story. That's why you see so many lower ground floors in Victorian properties. When you run the numbers on this, and I did because I'm super cool and have no life, that thing is working bang on the limit. When we talk about ultimate limit states and serviceable limit states, this is serviceable. This is right on the limit of serviceable. There's no factor of safety in there. So if you get any subsidence, any movement, and that thing wants to move, then you crack in straight away. I think it's a beautiful bit of engineering, and a lot of the practices that the Victorians used back then, we still use today. We picked up a book recently that was about 150 years old, and the equations and the recommendations in there are still the same as we apply today. There's not much change in terms of how we approach engineering, but I do like the Victorians for this, and they did lots of other great stuff for this reason that are still applicable in building regulations and that today as well. Ground movement, landslip and subsidence. what you're seeing now is subsidence. So subsidence is basically a weak spot in the ground. And a weak spot in the ground could be caused by anything. It could be old mining or a tunnel in the ground that's collapsed. Most typically, you'll see it as a leak in drainage or a rainwater pipe that's leaking close to the building. That causes a soft spot in the ground, and then the building wants to just basically slowly start to fall into it. And that's when you start seeing crack patterns within the building. And cracks are all cracks. I like them. They tell you where the problem is, especially in masonry. Cracks are terrible in tension. Masonry is great in compression, but it can't handle tension. So, you know, if you got a crack, diagonal crack, it's either something pulling it from this side or something pulling it from that side, and it tells you, it points to where the problem is. And when it points to where the problem is, it's usually a tree or a drainage run or something similar. And if there's nothing obvious there, then you need to start looking further afield and go, okay, what else do we have here? Is there a drainage run running through that we don't know about? Is there any underground mines that we don't know about? So this is more about more applicable to existing buildings, how you do it. In new build now, you would do a soil investigation. We know what's going on in the ground conditions. If we're coming on to, we call it a brownfield site, which has already been used, we'll do boreholes through. And we can do boreholes 5, 10, 20 meters deep, maybe more, depending on what the structure is that we're proposing to build. And we'll have an idea of how deep we need to go over our investigation, depending on the type of structure that we're going to build. And we'll roughly know, okay, it's going to be piles, okay, it's going to be shallow foundations, and we'll suit a soil investigation to suit what we need. Landslip is removal of a portion of the soil from underneath the building. So you're basically undermining the building and it leaves the building exposed. And this is more applicable on sloping sites, I would say. So we do actually design for this in new construction. It's called a slip plane. So you take those properties of the soil and you look at how rigid it is. And if that whole section where the building is wants to slip and wants to move, and we call that a slip circle. So we design for that as well. You don't often see that often, but I mean, if you, like, let's say flash floods, it's more applicable to that and there's a danger of that. But I think if you're in that region where you have history of that, you would know for that risk and you would design from the off anyway. And then that brings us on to A3, disproportionate collapse, which I'm going to just read this and say, the building shall be constructed so that in the event of an accident, the building will not suffer collapse to an extent disproportionate to the cause. Now, I haven't put any further info up here on my slides, and this is my last slide, because this, as I think most people will know, this is Roland Point. This was a 22-story building that collapsed, partial collapsed in May 16th, 1968. Ivy Hodge woke up one morning, lit a match for a kettle, and blew out 2 corner walls from her building. She was on the 18th floor. It took down 4 stories above her and 12 stories below. I remember I spoke to Joe about this a while back, and he thought, because this changed our building regulations for structure, this brought in disproportionate collapse. When we talk about disproportionate, the cause of collapse, a gas explosion in someone's dwelling, should not have caused this extent of collapse. So we call that disproportionate. And it massively changed our regulations and how we approach buildings. Joe was of the opinion that it should have had a bigger effect on fire than what it did. It also should have changed your opinion on how you look at fire as well. But the impact for us is that, yes, we can know we have to design buildings so they are resistant to disproportionate collapse. Now, in concrete buildings, the steel buildings, the steel elements within them, like the rebar within the concrete, are great in tension. So even if you do remove a column, remove a wall, do something there, then all that tension, providing it's connected properly or it's lapped properly, it's great at redistributing. And I remember going on a blast course at the SPHStructures, I think it was last year, year before, and they were talking about blast resistance of structures, and it was blast engineering it, proper geeky. But they used loads of examples from the 1980s and all the IRA bombings at pubs and all this kind of stuff. And they were showing examples of buildings that were still standing. And there was one photo of a RC column, all the concrete completely blown away, but the reinforcement was still through there. And I was just looking at that thinking, if ties aren't the answer, then we've got the answers. We know how to build. These things work really well, and it's still standing. And I'm sure they either demolished that building or temporary propped it, removed that section and rebuilt. But that's how we're resistant to accidental load in the event of an explosion now. So we structural engineers, when we talk about accidental loading, it's predominantly a gas explosion, and we basically play Jenga with buildings now. So if we're not tying it through, then we have to play Jenga. So masonry wall construction, you can thread rebar through. It's not the best construction technique. A lot of people don't like it, but it might be used on, say, 2-story masonry schools as an alternative to a steel option. Most people are going the CLT route now because you can tie those panel systems in a little bit. But I think if you're getting above, say, 4-story in residential, so basically 5 stories and above, this becomes an issue, depending on the consequence of the building. And we talked about consequence earlier, consequence classes. So 1, you don't need disproportionate collapse. Agriculture buildings out in the sticks somewhere, you don't really have to worry. Class 2 buildings, 2A, basically residential up to about 4 stories. You can build them out or whatever, but you're adding horizontal ties. When you add horizontal ties, you're just making sure it helps with lateral wind load as well. It just makes sure the whole thing's tied together, acts a bit different, acts a bit stiffer. You're good. 5 stories and above, you're going class 2B. And then this is where you're going to start adding vertical ties through. Or this is an approved document A. We take that from here, and then in approved document A, 15 stories and above would be key element or risk assessments. And so when I started looking at existing buildings, because there's not that much here, and this is going to feed in to the afternoon session as well, which is why I kind of want to end here, is that how do you apply this to existing buildings that aren't compliant to disproportionate collapse? Where are you drawing the line on safety? How are we supposed to appraise buildings? So this is, we call this a large panel system, and it's basically concrete precast panels stacked one on top of the other, and it's like a house of cards. There's a lot of these still standing, and so understanding the risk in relation to these is very different. And just going back to Ronan's point, they reckon that when you read the report, they reckon if it wasn't for a gas explosion, the wind load would have got it anyway, because it was under design to wind as well. So, and I think that's what they saw at Barton House in the one over at Bristol recently, where they saw cracks at the upper floors opening. And it sounds like that was, this is just me guessing, but it sounds like that was fatigue. The building's moving in the wind, it's opening up cracks at the higher level. I think that was probably more susceptible to wind loading than anything else. And that's probably why they need to strengthen works in. But again, that's looking at form of construction, how it's built, where the risk is. And that should tie us into this afternoon session. I hope that helps.
Real. Thank you. Thank you so much, Sean. There are questions. We have time for questions, don't we? I think we're going to break at 1:15, so I can try and get through as many of them as I can. If you're happy for questions.
Yeah, can I just say, it feels really weird just talking to myself for 45 minutes with you don't know how you're getting on. You don't know. It's just, I was like, all right. At one point, I wondered if you guys were still there.
Mate, you sound like a lecturer. That's the life of a lecturer. Is anyone still there? And is anyone really listening? Is my career. Anyway, there are tons of questions though, so thank you for that. Loads of people saying thanks there as well. Yeah, for me, like, structural engineering is terrifying. I don't know if you guys appreciate how terrifying it is for non-structural engineers, but the thought of these calcs being off by 10% and designing right to the limit and then it being wrong is terrifying. And a really interesting point about blast engineering from me there, because my master's degree was explosion engineering, so we studied the effect of it. I never knew that Ronan Point would have gone anyway because of the wind. I didn't know there was an inherent fatigue flaw within the building, and it was just the explosion was the thing that highlighted it. So I learned something really useful there.
Yes, I'm going to come on to that in the risk assessment later, because I want to touch on that as well.
Nice. Okay, cool. Well, let me smash through some questions. I've got some of my own and some from everyone who's dialed in. So let me do a mix of both. First of all, let me pick up on a dead load, live load thing. So you mentioned dead loads as the weight of the structure, live loads, snow and people. What about things inside the building? And it was Andrea, I think, asked about if you put a library in a building and move it. And it reminded me of the old story of the library that sank because they didn't put the weight of the books in or something. It's like an old architectural thing. So where does that sit? Things that you have in the building that you could move, but don't generally move over a transient time.
So basically, libraries would fall under E, storage, and we take stupid high loads for storage. And if you are, so you can retrofit an existing building to make it a library or a storage room or an old archive room, for instance, and we would have to reinforce that floor. And we would tell them, you can put your library here, nowhere else. And so if we know where the bookcases are and that, it helps, but we would generally apply the same load through, and we would assume books, floor to ceiling. And we go, great, we're going to design the whole floor for that. You're good to go. So they can move it around within the room, but not within the building.
Sure. So if you did a change of use of building, there was a question actually. Let me pick this out because it highlights it better. Stand by. It was, is it easy to convert an office to a resi? Was the question from Paul. I think what that probably means is that the resi has a lower loading. So is that easier to do? But I suppose wider than that, if you're doing any change of use, do you have to redo the calc from scratch and potentially upgrade and do that? Or is it easier to do a lower load and you just maintain what's there? Presumably you don't take structure away. How does that work for retrofits?
Okay, so office is 2.5. Resi is 1.5 imposed load. Your dead load's still going to be the same on both, so that doesn't change. So basically, you're gaining 1 kilonewton live load back. Now, if you're just doing a straight conversion, straight swap, office into resi, you're not normally going to check anything because you know the structure can already take a higher load. The problem then comes if you're extending the building, adding more floors and doing something like that. Then you're trying to offset the load that you've saved here, throwing it up there, and then you might need to do a check of the calcs and see what needs strengthening and go from there. But then you're creeping back into assessment of buildings.
And how valid are those? Because it was like a range, wasn't it? It gave for the loads, and then the underlined one is the accepted sort of minimum. How deep into that would you go? Are you at the point where you're weighing chairs, or are you kind of accepting a range in there and making assumptions off that?
So for instance, 1.5 kilonewtons per meter squared is about 150 kilograms per meter squared. So that is 2 of me hugging each other on every meter squared on every floor in a house. It's still a lot of load, but it will cover beds, baths, the whole lot. You're not really going to exceed anything like that. When you look over the history of the like that load's come down a lot since like 1930s. I mean, this is where you go back into existing buildings, you find hidden load, so to speak. You'd find the structure was designed for 4 or 3.5 or whatever. But oh, great, okay. And then that will help you in your assessment of the building and sometimes loading foundations or loading walls up as well. But there is, new build is accepted, existing, people pinch an inch from the safety factors to make stuff work. And I'm touching on that this afternoon and why we don't do it.
Sure. Okay, perfect. Do you take account of, as you were talking, I'm thinking about a job I'm working on at the minute where they're retrofitting a gym into an upper floor. It's like a communal gym thing that they're going in. Would you take account of a sort of drop load there? So, I mean, it sounds like a minor question, but if you're in a gym and you drop something from head height and it's a weight plate, is that taken into account as a sort of dynamic action, is what we'd call it in fire, rather than an imposed load that is assumed to be linear, if you know what I mean?
Yeah, so you would naturally take a higher area load. I don't know what it is for gyms. Let's call it 5, for instance. And then like you said, you might have a guy we've all been in the gym, the guys overhead, throw the weights down. And we design for a point load on there anyway, which might be another 5 kilonewton point load. But the dynamic action of that, I can't, guys on the call, correct me if I'm wrong, if you know the clause in the codes where it says to do this. The only thing I can think about is maybe in vibration, you would maybe add that as an additional load case and go, right, if I'm getting a 50 kilogram, 100 kilogram point load dropped from 3 meters high, what does that do with my vibrations? So I'd probably do an additional calc and check on that. But that'd be about it, I guess.
Good. I'm glad you said vibrations, actually, because it's a note that Peter made in the chat about vibrations. And somebody asked a question, I don't know who he was responding to, but I used to work in an office in Holborn and it was right over a tube station. And what I found was you'd always feel the vibrations. But if I was in the office on my own, you'd feel it more so. Now, is that because there's less load there that is offsetting the vibration? Do you accept there's always a resonance in buildings and it changes? Or was that just a dodgy building I worked in?
It sounds like an old building, but also if you got more mass on the floor, then it's more dampening the effect. So it's counteracting the vibration effect. So so if you've got 50 people on your floor, you probably wouldn't have felt it as much as if it was just you for that reason.
Yeah, that makes sense. I'd never considered that until I saw Peter's comment and you just said there, but there was this standard resonance that was always happening because tubes were going past every couple of minutes. But I always used to wonder why it was different throughout the day, but it's because it's dampening when there's more live load in there, I guess.
Yeah, I wouldn't say it's a dark art. I've done some vibration calcs. I know enough to check the basics. Stairs, you'll see feature stairs quite a lot. and that's normally one of the critical factors through there. So you'll see like bespoke cantilevered stone stairs coming through, or winding steel stairs and stuff like that, and we have to check vibration on that as you're walking up or walking down, or two people going vice versa. So and that gets that's a bit technical, but yeah, that's what I would consider.
Yeah, I felt like a proper structural engineer there, not claiming that I am, but I said live loads and dampening, and I was quite proud of myself. So yeah, I'm learning stuff.
And you used them as well, mate.
Yeah. Okay, cool. More questions. One from Dana. Can you check retrospectively these calculations if you don't have the original design info? And how do you go about doing that? So if that is lost, it's in the ether, it's been lost forever, can you retrospectively do these calculations, and do you?
Dana, what did we say about nice questions? Simple questions. So a lot of existing building stock don't have calculations or drawings. So typically they only kept them for 15 years. Your building control bodies normally kept them 50 years. Then if you're lucky, they went on a microfilm and they're stored somewhere. Most of the time, though, you're working without any information. Now, if you go through the code, we're creeping into assessment of the existing buildings kind of stuff here. Now, there's an international code that talks about this, and there's a thing called a plausibility check. Okay, so plausibility check. So you could look at an old building, and I could go in and I could roughly know which way the floors are going. I can even make an allowance and make an assumption, and I can roughly work out how much load is acting on, say, a ground floor wall. But if I'm working I could pick up the old codes, and the old codes say that shouldn't be working. I could put it into the new codes and they go, it shouldn't be working. So in that sense, I know that wall is actually stronger than what the calculations are telling me. Okay, it has to be. It's standing up. That's what's called a plausibility check, or you call nonsense on it, so to speak. So if you're doing that, that should trigger to get it tested. So I would go, right, test that wall. I know it's strong, it's stood up, there's no cracking, it's working fine, get it tested. And we would make an allowance for, say, the strength of that wall, and we'll take a basic strength, typically it is, but materials are typically stronger. We work on the base material. So even if you were to cast 1,000 bricks, they're going to fall within a range of strength. So on the bell curve, the mean is the top of the bell curve, and we take that strength for new build. On existing, we might work down here at about 5%. And we say, okay, look, we know over 1,000 bricks, they're going to work to this. This is the strength they use. But actually, that wall that we don't think is working might be other end of the bell curve. And we go, actually, it's really strong. It's great. Cheers. Thanks very much. But then at least we know. And then it's just documented, like, especially in the golden thread and stuff now, we've got to start documenting as much existing building information as we can on that. So yes, you can do it, but it's one, knowing what you're walking into, two, being ahead of the results. That's a big one. I've had results come back from steel testing that told me the steel was really weak, and when you run the numbers, the building wouldn't be stand up if it was right. So I had to push back on the lab, get it retested, and the retests come back what we expected. That's a big risk as well. So yeah, you can do it, but you just need to know what you're walking into.
Sure. Okay. But yeah, perfect. One last question. We've got a couple of minutes to finish up on. The reason I'm interested in this is because it's the inverse to fire, and I'll explain why in my session this afternoon. But if you're doing the calcs, you do these per floor, presumably, because it's cumulative down the building. So does that mean you are under specifying the upper floors because they're carrying less load than you are the lower floor? So is the strongest part of your structural design the ground floor, and do you under specify as you go up? Because we get asked to do this in fire for the same reason, but it works the opposite way around for us. But how is it for you guys in structures?
We work top down. So yes, we chase the load down, it's all cumulative. And then, but it's not necessarily, you would rather than you might have, let's say your top floor wall might be 100 mil thick. That might be working at 60%, 50%, maybe. Like there's not a load on it, it's roof, but you know, your wall thickness is 100 mil and the architect drawings, stick it in, it's not working very hard. It will take more load. As you get out in the building, that 100 mil wall, it might be 70% the wall below, 80% the wall below that. Ground floor, it might be up to 90%, or it exceeds that. You might have to kick it out to 140 mil wall. So you're trying to work within the 80% unity most of the time, because it kind of jumps up fairly quick after that, depending on what you're throwing on. And so, yeah, you're pushing it to 80, 90%, working what you can. And then it's your top 2 floors generally aren't working very hard. Everything below that, you're designing near capacity as much as you can then.
Yeah, no, that makes sense. Okay, brilliant. What we'll do, similar to the one earlier, there are more questions, but we'll have to pick them up after in this afternoon's discussion, or perhaps LinkedIn after. But yeah, lots of stuff in there, particularly from the fire guys. I'm noticing some names saying thank you. I know for me as a fire engineer, it's useful to learn this. So yeah, thanks again, Sean. Should we call that close of morning session? Have you got anything you want to surmise at the end, Sean, for how we've done this morning? Anything to finish on?
Don't think so. I think it's gone quicker than I thought. Enjoying it. I'm glad we're getting comments and we're not just sat here talking to ourselves. It's always a bonus.
Yeah, no, I think it's exactly what we wanted, which is this idea of like no stupid questions, learning stuff about each other's disciplines, which is the idea, isn't it? So yeah, going really well. Now this afternoon, I've changed my presentation a little bit following some questions this morning. I'm going to go through some structural fire considerations for how we determine period of minutes and things, because it was a really big point this morning. So I'm going to pick up that at 1 o'clock, aren't I? And then I think it's to the structures guys for the last session, isn't it, for your risk assessment, which is a good technical one for any of our fire guys. And that's where we pick up at 2 o'clock, isn't it? But 1 o'clock back on the second meeting invite for fire risk assessment and structural fire, I think is the plan, isn't it?
Yeah, so I threw up the link for the afternoon session right at the start of my presentation anyway. I'll throw it up again now. And then I'm going to leave that on for 15 minutes, close this. Margaret, I have just saw your comment on the recording. The recording normally generates itself once we've finished, once everybody's closed. And then, yeah, then we'll hop across to the new link. I'll throw it in the chat, copy it, new link, starts 1 o'clock. Joe, hit the ground running. We'll go from there.
Spot on. Sounds good. Okay, cool. Hope to see some of the folks back for the afternoon. I know there'll be some more folks on as well. So thanks everyone for this morning, and thanks Sean. I'll see you have some lunch. Speak to you shortly.